context of where you're asking it for a completion, and it makes a prediction about which of these different candidate proposals is the most useful one to add. And so we train this small model here, and then it does the actual selection of which information do we want to add in. Just to sort of give you an idea, if we take the default only giving it the prefix of the code, then we get this, say, 59% success rate of predicting the rest of the line. If you take an oracle, which in every situation knows what is the best rule to invoke or what is the best proposal to use, then this gives us an upper bound of how well we can do. And it's quite a lot higher, which at least says, you know, there is some information out there that if we could give it to it, if we could locate it, it would help a lot. And then with the rule classifier, we're able to get it about 68.5%. So still some improvement. I will add that a good part of this improvement comes from also using context after the cursor, which is maybe not the most surprising thing, that it would be useful. Okay, and then let me just go to the third part. And this is about program execution. We're working with these software systems that are incredibly complex. You know, when they execute, it's a very complicated system. And so what we're looking at here is problems that challenge our ability, challenge our machine learning models in order to do this kind of reasoning, if you will, about program execution, but also doing it in a way that leverages the strengths of machine learning and not only sort of the weaknesses of it relative to like just a normal interpreter, for example. So when we think about this in terms of reasoning about execution behavior, one way to think about it is in terms of errors and bugs that you might have in your code. And so there's, there's some kind of bugs, if you think about it, which are just kind of like a simple typo, like somebody meant to put B here, but they put A, and so it's a one-line replacement. But there's nothing wrong with this unless you have a test and an assertion here. On the other hand, you can see on the right side, we're going to get a runtime error in the second case because we potentially have, you know, a negative number that we're trying to take a square root of. And the point is that the argument that we're making about this as a task is that trying to predict when you're going to encounter a runtime error in a program is a good challenge problem of saying, okay, it requires some understanding of what's going on in the program for a machine learning model, but it's also, you know, sort of easy to evaluate and sort of more contained and easier to build a benchmark around it. And just to sort of like point out that this is not a solved problem. You know, we can all think about sort of executing a program. We know how many steps it can take, and you know, you have to track state across different functions and across different variables, etc. And also there's been observations in some of these large language model papers, like the Austin et al. One I'm citing here, is even when a model has learned to do programming by example, so you can give it some input-output examples you want, and it's pretty good at predicting a program that satisfies those examples. You can probe it and sort of come to the conclusion, actually, it's not really able though to execute this program to say, if you gave it this input in this program, what would the output be? So there is some sort of lack of full capability here. Yeah, so going back to the runtime errors task, we created a data set based upon a CodeNet, previously this CodeNet project cited here, had a bunch of programs from competitive programming problems. And it's a pretty large data set, and it's nice because these programs are small enough to be self-contained and you can execute them as well and see what happens. And so what we did is we took this data, we executed them with just one example input. This is a limitation here, but and then observed whether it encountered a runtime error or not. And then this gives us the data set of, we have programs and we have, was there a runtime error? And if so, where did it appear? This is just an example of here what it might look like in a very simple case. The programs are a bit more complicated than this. So the sort of the modeling approach that we've been looking at here is trying to see if we inject more domain knowledge about the execution behavior of programs, can we get some improvements in this kind of task? So what we have here is a control flow graph. It's very simple. There's three statements here, and this shows the sort of the possible flows of execution in the program. You start at the first node and you can either go to the second one or the third one. If you go to the second one, you're going to loop back. And if you go to the third one, you're just going to stay there. And so the way that the model is going to work is we're going to take some inspiration from attention models and some inspiration from graph neural networks. I'm not going to go into all of the details here, but the rough idea is we're going to maintain what we call instruction pointer attention over the nodes of the control flow graph. And this is saying at every point in time, we're going to have a probability distribution over where the model thinks it is in a soft way in terms of the control flow graph. And then associated with each of the nodes in the control flow graph, we're also going to have a hidden state, which if you want to think about it intuitively is kind of saying like, what is the set of all values of variables at this point in time if I were at this control flow node? So it's going to execute through time and through control flow nodes. And for each of those, we're going to have one of these hidden states and one of these instruction pointer attention values. And then the quote, quote, execution step is going to say, okay, to advance from one time step to the next, we're first going to say, okay, if we take the code, which is denoted X here, and the current state of values represented as a hidden state, and then we learn a model here of mapping the sort of the one step of execution to get an updated hidden state representation of what's going on there. And then we're also going to, at the nodes that have multiple outgoing choices here, there's a branch decision, and we're going to make a prediction about which way is the control flow going to go. So sort of like in a soft way, if we were at this node, we make a prediction about, are we going to go to node 2 or node 3? And then this is sort of like the soft branch decision. And then from this, we're going to do kind of what you would expect the natural thing to do to update the instruction pointer attention would be, excuse me, which is to say sort of multiply the probability that you were at this previous state by the probability that you went from this state to the next state. And then this gives you the transition probability of going into the next state. And then you sum up all of the ways of getting into a node and you average the hidden states representing the values. Hopefully this is the most detailed slide. Hopefully it was at least somewhat accessible, but the idea then is, if you think about it, is you simultaneously have a belief or attention about which node in the graph, in the control flow graph, are you probably at, but it's averaging over all of those at the same time. And then you're simultaneously saying like, you know, if I would have gone this way, what would have the evolved state of the program be? If I would have gone this way, what would the evolved state of the program be? And then you're doing a lot of averaging of the hidden states along the way to kind of build this up. But I guess another way of saying this though is, if you did relax the attention to just be ones and zeros, then this would correspond to different traversals of the control flow graph. And then what we did in sort of the second part of this work is we said, what if we took this idea of kind of like learning these more abstract notions of execution and added some more model structure around exception handling? So now there's an option for the model not only to say, I'm going to go on, or like which branch decision am I going to make, but I also have the option to raise an error at each point. And then the other part of the work that we did here is we said, well, you know, one of the interesting things about machine learning models is they don't have this hard-coded interpreter structure to them. It's all going to be learned. So we're going to give this model examples of sort of whatever kind of input-output examples we want. And then it gets to use this model structure in whatever way that it wants to. It's not predefined to be like step-by-step constrained to how actual programs execute. It's also not constrained to use the meaning of the values in the program in a traditional way. And it comes up if at some level of like, here is the input, here's an embedding of that input, and then this is what sets the state inside of these models. And what we played around with here is we said, well, so what we can do with these models is we don't even need the concrete values as inputs to the programs. But if we have descriptions of what standard in is going to be, then we can add this as a sort of the value of some state in the program. And so then we can play around with these ideas of execution, which are like, at the highest level of what does it mean to execute a natural language description of the inputs to the program. So we played around with this kind of space as well. Of once you sort of move this notion of execution into the neural domain, if you will, there's sort of interesting spaces, I think, to play around. Just to give you an example of what this looks like then, we have the original model. Okay, so there's two different executions here. Let's say the first one is without using the description of the inputs. And along the x-axis is we have time steps of the execution state. And then on the y-axis, we're showing the attention value for the different nodes in the control flow graph. And so you can see it as kind of going through sequentially this program here. It's just a sequential program. And then there's over here some looping happening. It's not one for one, sort of like time steps of model execution, but you see it's kind of like going around in the loop. And then eventually the second to last row is this exit state. And the way that we determine if there was an error or not is we have this exception state as well. Once you raise an exception, then you go to a special node that represents an exception occurred. And when you add the resource description here, you see it's done a job of understanding the sort of the execution is going along. And then at some point, it starts to put a lot of probability on this exception state node. Okay. So that's just kind of a rough idea of what's going on. And so, yeah, so that's kind of all I wanted to say. In recap, there were these three challenges, which you could think of either as limitations or research directions, or actually both. What is it the developers are trying to do? How do we get the information that they need in order to do these tasks? And how do we operate given the complexity of the artifacts that we're working on here? There's going to be limitations for machine learning models. It's going to be really hard to have a perfect understanding of what's going to happen with everything that happens with program execution. And so I thought sort of the SEMLA crowd, the point that seemed interesting to me is that we are nonetheless seeing these tools be useful for assisting software developers. We are moving forward in building these tools. But all of these problems are not fully solved problems. And so this seems to be kind of going back to the sort of the limitations of the models and understanding kind of like insufficiencies, maybe is a good word I hadn't used before for this, but it's sort of an interesting space to be thinking about those same kinds of problems too. Thank you.
Thank you, Danny.
Thank you.
Have a few questions from the audience.
Thank you. I worked in a project trying to find out what the problem solving and strategy of the developer. But first of all, I want to know if you think that the first and the second challenge, the result can be combined in a way that we can use it to do knowledge transfer. So if I ask like the students, the whole group to work on some problems and I stack this information, maybe provided with a summarization of what they have done to be transferable to other developers, and most on like a machine level thing they follow.
Interesting. So if I understand right, you're kind of saying, how much can we elicit from experienced developers of like, what are the common things that they're trying to do? And when they're doing those things, what are their information needs? Yeah, I think it's definitely an interesting direction and question. I think maybe one of the unstated assumptions that I've kind of been operating on is it's hard to get developers to change their behaviors. And so a lot of when thinking about like inferring what developers are trying to do, I'm thinking about it in the lens of without asking them to modify their behaviors. And so like, you know, we can look at what bugs they're filing and what PR discussions that they're having. But I hadn't thought so much about, you know, like what could we prompt people to be doing or like to create these workflows or to sort of like annotate what they're doing. I think there might be some interesting stuff. Thank you. Oh, sorry.
So I have a question about so I just wanted to know if you could communication for extending the contact and meeting for these people. Because like you know, it's only very long time I have like something to do extend the contact too much instead of like helping them about the and also like for this situation like the program to tell the function these things is necessary but the difference is the more they have this and more how it's
Yeah, that's a good question. So for the experiments that we did, we just used the Codex API, which I think has a 4096 length context window. And the answers that I'm going to give you are all conditional upon the model was trained with that. So that's what it's been trained to do. We did play around with giving it less information as well, like it was trained with 4096 tokens, but let's just give it half of that as input context. And as far as I remember, that made it work a bit worse. Like, you know, it was sort of the monotonically improving as you gave it more of a context window up to the context window that it was trained on. But I think there was also diminishing returns, if I'm remembering right. And so what we did in that work was we literally just carved it in half. We said there's 2048 for the context before the lines, and there's 2048 for other things. There certainly were cases where, you know, you can sort of put in the wrong thing, or, you know, maybe you find a function that seems related to what the developer is going to call, but it's the wrong function, and then that obviously causes it to behave worse. But on average, we didn't find that it hurt too much, no matter what we did. Like there were some cases where performance went a little bit down if you had a really bad sort of extra rule to add. But I think it's, yeah, I didn't find that to be a huge problem. And maybe that's just because it already had the 2048 previous tokens to work with, and then you were just adding some extra stuff in before.
We have one last question for the clarification. But then I think you can discuss in this way because you're only going to down for yeah.
I think we are very different about so actually very interested in how we manage to learn make a difference. Another way is finding some language because one big challenge where we're constantly manage to kind of be working on through that activity report. So for example, what is in the and especially if you want to be talking about the big challenges with the fundamental of whether it's not to be
Yeah, so just to clarify, we're not able to perfectly learn to execute these programs. There is going to be a loss of accuracy and going from like an actual interpreter to these proxies that we have. And then I'm sort of just setting this up as it's interesting from a machine learning perspective to try to push on this of saying like, how can we move towards models that are able to do this? In terms of the question of like, how do we train such a thing? There's two different variations that we've worked on. There was this the first paper from 2020 where we worked on this, which was looking more at just learning the execution itself, or learning the execution where we blanked out some information about the program to make it kind of like a harder task. And there we just gave it input-output examples. We said, here's the control flow graph, here are the inputs, and here are the outputs. Now, machine learning model, optimize the loss function as best as you can in order to produce these outputs from these inputs. So it's a machine learning model, but it just has some structure that resembles the sort of the knowledge that we have from the domain. And for the runtime errors task, we just trained it on, here's a program, is there going to be a runtime error or not? And that's the only supervision that we provided. We never gave it sort of like step-by-step supervision in any of these cases.
Thank you. We have 20 minutes break, and 11, 10
Hey, thank you. Just a quick question. Is that the error prediction is a static code, not a runtime code, right?
It's, yeah, you're just
Social activity is a rule. So the next session which will be short, a little bit shorter, because we are 11. But
we have lunch. But yesterday we had shorter lunch.
yeah, maximum we can do that. It doesn't. We're half an hour late.
Yeah. So we have industry messages.
We will be like at 1 o'clock maximum.
I was thinking that maybe I'm missing something, maybe it can be done through machine learning, but I said that psychology also like you have to define it. The model cannot define the context in that way, right? But it has to be like you have to manually and think about it and have the developer perspective as well.
Yeah, it's an interesting question. I think we've done some early work, like, because it's really a computational question. We had models that could attend over 100,000 tokens, and I think we kind of believe that would be the best thing. The model will just start to ignore the things that aren't relevant, and so that's the question. Really becomes like, what do you, in a computationally efficient way, choose a sparse subset of the input to provide such that it picks off the most useful stuff? But it's always hard. Also, these continuous boundary gradient don't work anymore. So I think it's a harder technical problem.
And because now we were looking at use cases that were dependent on the class and project size levels, like this for next time more. But I will definitely give you.
And just to be clear, it's not a.
Yeah, but you have more.
So complicated. Like, we're never gonna.
I'm sorry.
That's kind
Because
of,
it's so relevant.
yeah. But that's what makes it fun, like. So awesome.
Very briefly. We tested there. It also seems.
Actually, triangling is because the actions that were actually predicted by the models. Doesn't make any sense, but it's also because of the data. And as a researcher, like we said, we have to that so when you don't have a data to train the model, how you can expect it to generate a patch. Right? So
Oh, yeah.
you have the same, even though like I know like have a bigger data system because of one company. Do you have the same problem that it was, or is
But,
something with the model or the data itself?
Yeah, I mean, I think there's a lot of these points are part of it requires sort of understanding. It combines many of the things.
I have a bit on there.
It requires
some,
like
it's not as
data
complex,
execution,
like some program generation,
like
like SQL
are really hard. Like
or a
see the test failure,
database query generation.
or like
And
how do you know what's the developer?
from the natural language.
It's more difficult.
Well, like you would
So,
ask
I don't know. I think it's a great
basically
problem.
a database query in natural language.
Thank you,
Like,
thank you.
how many students got the providing their exam, but the approach I developed was very like,
Way to find out.
it was more like, it's just like, it's not one model, so when, first you define. So, but some other people were working on it.
Yeah,
and when-
not sure.
But doing that is so complicated, because you can't,
That's got to be. It will say like the chat.
Yes, exactly, provide the coverage.
Yeah,
because maybe
but
the
it's
user
like questions.
has the parameters that should be passed.
But
Kind of.
I had like tried some stuff for like end-to-end
with the
things,
boundaries of
but
the-
it's just so complicated.
Yeah.
So I was just thinking
Failed
that
to
maybe
get it
you
working,
use it
that-
for the providing
in
the
the
context.
context of like.
No, it's a great idea. I think it's more of a data
Difficult structure.
problem,
Yeah.
just like where do you get
It's like
the large
the-
amount.
The researchers are like, well, it's gonna take months to get something that maybe works.
Because I had a follow-up question, because when you're in the unit.
It's impossible to
It's a
measure.
stop or driver.
Space is like.
You're
You have to
between
define
and the
the
scaffold.
space in which you have
As it is not done, I think it would be the next step for the
Yeah.
previous.
Yeah, so it's like. it's
Thank you,
really
it was a great time.
I know that there's like big data sets for getting like. 30s, 70s, But still, you go outside of the domain, like. It's very easy to have like a domain.
Like just like natural language is just like.
Yeah, that kind of stuff. So as soon as you have like complicated queries or stuff, that's not like, oh, how many people have more than like three bananas, it's like. It becomes,
So I'm like facing very limitation.
but that's why I thought it's interesting, for actually.
Within like intuition. So like we're going like to find another like actually find label networks with their testing.
Yeah, there's a lot of like assumptions.
Like having test. No.
Yeah. Or even during a stock, I was
Or
thinking,
even do you think that it.
sometimes I write code and I don't even
It's like a good idea.
know where I'm going with. I don't have an intent, My intent is just to explore something, and maybe my intent starts with A and then becomes B and C.
Again, like kind of like unless you have some like question for you like that.
Yeah.
How much information is like specification?
Right, yeah, reduced scope,
I guess you probably learn something.
yeah,
But then that's something.
right. Well, yeah, still,
Thinking about corner cases, or like identifying what those corner cases are.
it was a fun project.
So you're doing something.
We already like tried with like Python and.
Like what?
We turned some
Log
but to me,
generation.
it's like maybe.
Like based on.
Train on the data and like the data also that we have exam. It's from GitHub, like the test is that it's general. It's very similar to the like the ground. To me, it's like
Like,
maybe
are they
like
think what the
memorizing.
program's gonna output?
Like this. So the reason that we are like going to like
Okay.
So yeah.
So you want that one.
Yeah.
Code gen, okay. Yeah, I can find you.
I mean,
What's the goal? Know where you should put like. Or like. Okay. Right, okay. So that's like a fraction of the intent of a programmer, right?
Yeah.
Kind of, yeah.
So it's like.
Right. Yeah. So even knowing where to print logs is smart.
like one way of describing something uncertain, so it's right.
Yeah.
Very.
Hi, how are you? We have, so there's two of them.
Yeah, and then we put it in the design.
You can pass.
Yeah.
Or you take this one.
Yes. This is.
And do you have any kind of machine learning?
Yeah. Another thing we need to do some water.
Yeah, that's like.
Some water. We need to get some water for the speakers, I think. Yeah.
Some of this, like the temporal.
Because it just comes to might be my imagination coming along with conscientiousness.
Okay. Yeah,
Try to reason along the mind logics.
Yeah, that's what it is. Okay. You're not.
we can put this here if they want.
You're trying to.
Are you?
Yeah, let's kick it up.
I think I saw your profile one time. But I did not even understand. Maybe I didn't search it. Yeah, but after listening to your topic, it's really in line with the kind of things I like to do. It was really enlightening.
What do you?
Right now.
Yeah, so we have two, like this one and the other one. So I think every two of you can share this one. I have one.
And then CPS. So companies don't want to build pipes without this thing. So best intentions of use onboarding the right sense to pick up new suppliers that technology processes.
Yeah.
So we can keep from that process.
It's not the first time.
For example, my Dutch was handed over to me. That is the initial point of this kind of stuff.
Right.
Because if the original purpose of the
Right.
manage. There is a problem.
Right.
Then when this thing is done.
Oh, yeah. No, but as you know, as
how is the
research
research
doing nothing, like we're talking, just mentioned this kind of.
because we need to keep ecosystem,
Yeah.
even the best that we have observed. Great collaboration. Developers tend to writing so many times different songs.
Oh, yeah. Yeah, well, it's more fresh.
Fewer people.
Where do you work now? Are you still working for? Oh, okay. I see. Okay.
Then we capture requirements, feedback from end users.
Yeah. Okay.
For example, of Microsoft.
It's like very different, like research, Morgan Stanley, back to.
Care about the end users. It might be we are missing all the requirements.
Yeah.
Should we have complaints and all sorts of things. Capture this feedback, try to see.
Yeah.
Then now, like, now that we kind of well understand the system. So the main intention is
But yeah, it's a good time. I heard like mixed things about Morgan Stanley. Like it depends which, but it's a very big company. So Yeah, because I think there's a lot of machines.
And also I use this kind of like feedback and direction. I use this graph.
Yeah.
I put one of the professors and distributions like on the social level.
Yeah.
Those are the kind of things I use to identify some layers and those. That's just like perhaps how you can enforce and make sure this kind of people are not really like included. Everybody is important, but unfortunately, the players.
Yeah, I mean, that's especially very interesting as well.
Yeah.
Research.
Are you on the
No. We can talk about this. Yeah, daily. That's a good point.
I didn't want to say it. But it couldn't actually got it on the side.
Well, you know, like when I studied at SEMLA, I did a master's, and we weren't even using it back then. We used like this, yeah. But it's like the standards of code quality are much like low. So it's like you just push stuff, you know, you just push stuff. But it's a good topic. Even those things, small tools.
Yeah, so maybe
Oh, yeah.
That's way only we would prepare like certain things.
Even like other various other tools that I would use for like submission. I never did that at school, you know, it's like the like database UIs, you know, that stuff. There's a bit of a okay. Yeah. Sure. Yeah. Well, unless it's, you know, it's kind of similar, but then there's all the packages. But there is all this practice. Yeah. Your call. Microphone sharing thing.
Salut. Salut. Hi.
Salut.
Enchanté.
Je parle français, mais on va
Ah, ok. Tu restes
do the whole thing in
à Montréal ou?
Ouais, ouais.
C'est quoi la compagnie? C'était
Eritus.ai. Ouais.
Vous faites quoi? C'est relié pour community growth? C'est
Ouais, c'est ça. C'est un petit pitch.
tu veux parler de micro? Moi, je partage ça.
Ouais.
Tu veux donner le micro peut-être? Non, peut-être donner le micro. Oh, got it. No, that's it. No, it was. Except for what?
Hello.
Hello.
那个北一点啊，发的没得东西，对，那是有什么？对，
Mais c'est pas très grand, hein, pour tout.
Non, on est en 57.
Combien ça
17.
fait? 17. C'est passé c'est plus une start-up. Ce n'est plus une start-up, ouais.
Comment?
Ce n'est plus une start-up.
Oui, ben on est comme, c'est vague. Là, ça.
Working.
Is
it?
I don't see the line coming on.
Yeah, this one. So I thought that when it's in the mic, it should work.
Oh, I got something. 1, 2, 3.
That's already issue.
This one is working. I heard something. Yeah, it's working.
Hello.
1, 2, 1.
Oh, yeah, that one is
It's not very well. It's not going to work now.
So do you see the green light? Yeah. Can we just start?
Can you progress? It's -10 this year.
Okay, I think we can get started. Welcome everyone to the third and I think the last panel of SEMLA. I'm Dr. Sharafi. I joined the University of Montreal last February as an assistant professor. But before that, I worked in a finance tech technology for 5 years. So if it's gonna be any discussions on sorry, we'll see. We're going to have an interesting discussion about the basically from industrial perspective about the AI and ML into changes. So I'm sure that it's going to be very exciting and we're going to have a lot of insights from our panelists here. I am going to introduce them and then after that we dive into the questions. So here I have Sushmita. She's an AI architect for the AI factory team at the National Bank of Canada. And her team is responsible for deployment and industrialization of AI models in production. Following a master's degree focused on game theory constructs in applied economics and statistics, Sushmita has spent the last decade in various analytical and data-centric roles in financial service industry, like from initiatives for companies such as JP Morgan and National Bank. In her current role, she's responsible for designing AI model architecture that balances delivering value while remaining pragmatic, scalable, and secure. So, Nita, and then we have Eric. He's the lead data scientist at Curtis AI, a startup building tools to help monitor and grow online community. After a master's degree focusing on recommender systems at Mila, Eric has worked for the last decade as an applied scientist, ML engineers for various startups and large companies. So his work includes NLP for Dow Jones, Element AI, and Curtis AI, along with recommendation and supply chain forecasting for JDA. His main focus as an ML practitioner is to build efficient, scalable, and usable models in the context of application development. And then here we have Patrick Sanderman. He's a CTO and co-founder of the Think System. He is an investor of the Zikan technology and leads the development of Protector and Insight engine over there. He is actually a mathematician. So he got his PhD in mathematics from the University of Ottawa, and over the last decades, he met with leaders from different industries like Milo, IBM, Microsoft, US Department of Defense, and even presented in various AI and ML summits and conferences all around the world. And then last but not least, we have Emmanuel over there. He's a senior data scientist at Ericsson in Canada. He holds a PhD in signal processing and telecommunication from IMT Atlantic in France. And before Ericsson, he worked as audio software developers, analysts, DSP engineers in different companies, and even worked at Amazon Lab, working on the Echo Dot third generation. So He received actually Ericsson Impact Award and the spoke of Edge Computer Cluster project of the MyTax program, and he collaborated on various projects with different Canadian universities. So I welcome you all. Thank you for being here. And without further ado, let's jump into the question. So we all know that AI is growing fast, and we can see it everywhere now in different companies. So it has been reported that 9 out of 10 leading businesses all around the world are investing into the AI, but still only 15% of them, 15% of them have deployed AI. So I'm going to ask about, like, what are the challenges there? What is the problem with AI and ML in production? Why we cannot see the exact same growth over there as the rest of the development cycle? So you can take turn. You want to give the start?
Want to start?
Yeah, I can start. Okay. Thank you for having me here. I think we want to talk about challenge. It starts with the concept also of having AI into production, right? AI to solve problems. And I think there's a mystery about behind, and people don't understand very well what the model is doing. I think start from there. Before having challenge on data, quality, and also the scientists involved in development AI project is also one of the biggest challenges. I think there's a lot of challenges. Thank you.
So it's actually the question, I would say. So what we've seen is that like the models can work, and data scientists build the model, usually based on amazing papers and with great results. But those models have been trained, say, for example, say on ImageNet, and people have been training on that, which is the same data set for everyone. And almost the model becomes almost optimized for ImageNet without, not consciously, but like the way the architecture grows, almost made for that. But the reality is that the second you go in industry, you have not much data, and the data is like kind of probably not even well formatted, and lots of disparity between the quality of images. And what we found is that basically the model was trained, great model, great result based on 1 or 2 numbers, 2, 3 metrics. Usually validation metrics is probably like people look at 1 or 2 and then you're like really happy. Then it gets to the people that will actually deploy it. They look at it and then they like, they put their images or their data in, and then they realize like, this is not going to work. It fails automatically on a very basically common sense problem. Something that a human would be like, no human would ever predict that. And what we found is it's all about robustness. If the model is robust, then when it gets to that stage, then things will go much better. So I mean, I can talk more, but you share.
But yeah, that's kind of a good point. Maybe I can talk about my experience when I got out of school. So after my master's, I'd worked on, that was back in 2011, 12, 13, when, you know, the whole thing started getting hyped up. And when I got my first industrial job, the shift in what I was doing actually turned out to be like, hey, I need to kind of like build data sets myself, because the data that's there in the company is not like it's all over the place. The signal you're trying to extract is not always obvious. You know, it's not always like you're given some data set, you know, matrix X and targets Y, and then, you know, do whatever. So I ended up having to like label data sets myself, do a bunch of feature engineering with all the domain knowledge that I had from, you know, that working at that job, and then label like 500 points, and then train some like, you know, SVM to do the job reasonably well, because I had injected so much knowledge into the whole pipeline that I could obtain a model that was performing a very specific task, but fairly well, and then we could just, you know, plug it into the whole system. So there's that was a big perspective shift from academia, where you realize all the data, it's either not good, not there, or the task is like not obvious. So you end up having to inject a lot of your own knowledge into the process. and maybe before passing to you, maybe I can take a step back. And I think there's a lot of reasons AI doesn't make it into, let's say, the product. And I think one of the reasons is that, you know, when you have a hammer, everything looks like a nail. And I think, you know, product development still has to like lead with the features that you want the AI to do. And I think some companies, you know, especially like older, bigger companies, they invest a lot of money to say like, oh, what can we do with AI? But it's not necessarily directed specifically at some of the problems they're really trying to solve. They just like build these teams and they're like, oh, do something with the data, you know, and the executives may not know exactly what they're trying to do with it. Maybe you can talk about that.
I think from an industry standpoint, there are three major challenges. The first one, at least if you look at the banking industry, is user experience at the end. So any AI model or solution has to be integrated into some kind of operational process downstream. And that inevitably impacts the user or the end user. We have to be very cautious what we do in production, because we are answering to our clients, to our regulators, and we also have a reputation impact if something goes wrong. So that in itself is a barrier to adopting AI. The second biggest challenge that I've seen is the discrepancy between models that are developed versus models that are built for. Your development environment is completely different. Most of the time, you have a virtual machine somewhere. If you do not have sensitive data, you could even develop a model on your local machine with an MME. That's model code. It works. We try deploying it, and at that point, when you're trying to source data into a production environment, the data has to be reliable, as my colleagues have mentioned previously. And production code has to have best practices. You have infrastructure as code that needs to be set up, automated pipelines that need to be set up, automated testing, a full suite of automated tests that have to work. You have to set up application monitoring and logging separate from model monitoring and logging. And so all of these lead to a longer time to market. And what happens is that your business partners who are expecting AI to fulfill some need are waiting and waiting and waiting. And from the time funds are invested in the model to the time value is actually derived from it, you prolong that timeline. And so this generates skepticism. It generates reluctance and distrust of the model itself. And what ends up happening is that this becomes a barrier to large-scale adoption of AI. You often get this feeling of, oh, you guys have still not delivered. I don't think it will do. And the third important challenge, as everybody has mentioned, is data. You'll be surprised that when you develop a model, that model could come, the data for that model could be a CSV file from the business. It could be a text file. It could be an audio file. It could be data from a non-production grade database that is not even maintained on an ongoing basis. It could be data that's historical data that's sitting in an offline store somewhere that our production applications cannot even access. This model works, but then when we try to put that in production, where do we get the data from, right? So these three are the most important challenges, in addition to model explainability and some of the other challenges that other panelists mentioned.
Thank you. We welcome the audience. So, day today, when suddenly was a new project, do you see the serious study in comparison of different technologies to prove that they are a good solution?
I don't know about study in comparison, but usually AI developers will, my experience has been that it's better to start simple, and you'll usually see less experienced people starting more complicated. And I find that it's usually good for people to push back on like, oh, what's this? Can you solve this with like a heuristic or some, you know, like regular expressions or whatever? And then after that, if you can't, then maybe, okay, you start to research, you know, can I find a data set? Is there a data-driven way I can solve this and go in a like increasingly complex fashion? But however, this usually happens if you have like 30 experienced people on the team, or you have multiple members that can bounce ideas. But sometimes if you, let's say you have a team where you like hired like one data scientist who maybe has like is maybe like junior intermediate, then sometimes you can fall into the trap of like having that person try to develop something that's too complicated or maybe impossible, and then kind of having this feeling of like, oh, we failed to deliver for that kind of stuff.
Yeah, maybe I will add some more here. First, we are an example. We have a group called Gaia Global AI Accelerator, which is a core team which work with all the business units in the company. And as he mentioned, the machine learning projects have SME, what we call subject matter expert. The data scientist cannot grow project in the company, the machine learning project alone. It needs to have the subject matter expert. The concept of the software relying on the subject matter expert. The data science will come afterward. Thanks.
Yeah, I think when you start a project, I mean, like basically you need all the right people in the same room talking about the same goal. And also that everyone, whenever there's an iteration within the project, you need to make sure that everyone sees what the iteration was and also what it looks like and what the results are, and do this in an iterative way. And this way, maybe you start like with machine learning because that's the client, what the client asked, because that's important sometimes for clients to say they are working on machine learning, but also try to push like a simpler version when you can, or complement with machine learning. So there's always different strategies, but I think like with basically if you have everyone in the room, those solutions will come up quickly, because if someone is not a data scientist, they will say, well, I used to do this at my other company, and this is how we solved it. And then like the data scientist will say, yeah, but you can get much better results, and let's do a POC, and then the things kind of grow from there. So that's
Thank you.
Thanks. Adoption is a matter of trade-off between cost and benefit usually. And I think with the usually it take some time to decide if they will adopt or expect in technology. But with AI, there was like a new phenomenon, which is the fear of missing the train. Like many companies just started hiring data scientists with and investing with the fear of missing the train. But at the same time, AI models and this are software, but the software that is different from traditional software. So we developed for years and years expertise in how to do software, how to put something in production, how to test, how to maintain, how to evaluate the technical bit of our decisions. But AI, we don't have that maturity. And I think we mentioned data scientists or expert managers, that are people who should work, will have all different kinds of tasks and people specializing that task for software. And we didn't get the time to adapt all this to this new kind of software. So can you reflect on that?
Maybe we can start again. I think in my experience, I ended up doing more software engineering than machine learning, even though I was, really into machine learning in my studies. But I'm still kind of like a machine learning developer. But I ended up growing into, having like backend developer skills. So that kind of speaks to the fact that I think people who are really interested in machine learning and AI, they inevitably, if they work in the industry, they have to learn how to be a software engineer, essentially, right? But they kind of, and I guess it takes more time to grow into being both an engineer and a scientist, but eventually if you work in industry, unless you're like very insulated in a research lab in a huge company, then inevitably you have to become someone who's a software engineer and work with developers daily, right?
Maybe one word to understand. Yes, the development of the machine learning system requires a lot of expertise. It's obvious, but a data scientist alone cannot do the job. It started with SEMLA, as I said before, with data engineer is go to software developer, which has knowledge of code, and the ML side is very critical because having a working model is nothing compared to one stage where it involves how to elevate the solution more. I think it's all about software transformation. Software is one major component in machine learning deployment. But when it comes to data analysis, data input, data cleaning, yes, it doesn't feel appropriate, but it's critical. It's critical because we need to understand and how it's going to be orchestrated. This is not a very important factor that we make it. But at the end of the day, what we need is a collaboration, is a joint work, and teamwork to have a really good work deployed in an existing ecosystem. Because machine learning is not deployed alone for society; it's deployed into existing. Thanks.
Well, maybe I share a few, maybe a very quick thing. So I think the key, like, is maybe it's the right place to say that, but it's the key in such a team or such projects are engineers. I mean, you need an engineer because I have a lot of engineering friends, and we had a long discussion at some point that, okay, so I mean, you do so many projects and you do all those classes, but why are you doing this? I mean, you're working in a totally different field now, and all my friends, they all work in different fields. And then one of them told me, like, okay, it's all about when you go through Polytechnic, you just learn how to deal with projects and how to manage them and how to think about things. And this is basically what you learn, even though homework seems pointless at the time, but what you're learning is really, really valuable. And so those skills, the engineering skills, are basically what's needed, I think, for AI project to succeed. So the data scientist has its role to handle the data, train the model, but the engineers and the managers and the subject matter expert are also important. So I mean, maybe I'm yeah, I guess it's a good place to say that. So.
I would have a question for you, which is related exactly with what you're talking about. I share a point of view that the engineering skills are very important to validate the project to make sure it's going to succeed. And so I worked for a company where there were project managers. They were at the front line with the customers. They would define what is needed, but you don't have there an engineer. And because the project involves AI, there's a disconnect. So we were saying before that we need all the people in the room. I agree with that. What about the fact that a lot of industries are working with this workflow with the project manager and so on? I would like to hear from you all about that. How do you solve this, or what do you think about that?
I think one of the ways that we are dealing with it is to hire people to have some background in data and are data literate. So I understand that a product manager or a project manager role is semi-technical, but at the same time, considering that AI is a very special skill, having somebody who does not understand the fundamentals is going to result in requirements that are lost in translation, data issues down the line. So what we generally do is, even though it's a project management role, it's usually somebody who has worked in a data center role before, but is also very strong in their communication abilities. And is able to coordinate all of the various teams and stakeholders that need to be brought together.
Well, I think it's somehow like it's, I mean, what happened is that AI kind of rose and it became this big hype, and all the weight of this kind of ended up on the data scientists. And I mean, okay, so data scientists became lead of projects when they never managed projects, and everything was, they had to do it, and then they had to do presentation using Jupyter Notebook and so on. But the reality is that it's an engineering project. It's a project like every other, and the AI is one component. It's basically like it's a system. It's a module. So I think we can think of AI as this big thing. You just throw things at it, and AI will come out robust, and everyone will understand it. But that's not the case. It's a system, and if we think of deep learning or AI algorithm, it's a module, and if we treat it like this, then you just need to worry about that module. So data scientists and I guess the people managing the project needs to make sure that this module works within specification, that it's robust, that in certain environments it will perform, but it's a module. So and yeah, so I think so.
Yeah, very quickly, in Gaia, I think we have a manager, right? The manager will know exactly what the company is, what are the needs of the company, what are the strategies, the long-term strategy. I think it's required a manager with high focus. I think this is one of the key. It's a technical manager, sometimes I think it's still beautiful. We need a manager that is specific, and we know the goals of the company. Somebody who has vision, when it's all of that. I think our manager in Gaia, for example, has a lot of experience, has vision, you know the company, you know how to manage people. I think this is key.
Thanks. I think project managers can't be expected to know everything, obviously, and the details about AI, but I think from a project management point of view, it requires a slight reframing compared to software engineering, where it's like if I say, oh, can you implement this website with users and logins and some profiles and whatever, an experienced engineer will tell you, it's going to take roughly this 3 to 6 months, and we'll probably use this stack and whatever. However, for AI projects, it's not so much of a time deliverable, but more of a risk assessment, I find, where it's like, oh, we'd like to solve this problem with AI because we're not quite sure how to solve it yet, or it's a new feature. And then the main thing that has to be communicated is the risk that goes into developing this, because just even the data scientists' performance metrics are statistics, right? They're probabilities, right? So it's like you have to say stuff like, well, I think I can get a prototype within 2 weeks that'll be kind of bad, but at least it'll show you, it'll integrate into the products, and then maybe it'll take a few months to try to improve that model. And you have to say, okay, the spending 2 months on some AI project, that's not a whole lot of risk, but you have to be able to communicate, okay, what do we think we can achieve after 2 months? And because otherwise you get sunk costs, and all of that. So I think just from the project management point of view, is just the slight reframing of oh, it's not so much about how much time exactly it's going to take. It's like, oh, how likely do we think we can build such a thing within a given time frame?
Thank you. You brought up some points about the skill set of the people. Do you think the problem is that simply we don't have people with the right skill set to do the job, so that because it's more on the academic side to train those people, or we have the people need to organize them in a team that they work as a team together, so they can, every one of them can actually bring something to the table from their own background and education, what they have there.
I think the challenge with AI is that it is at the intersection of so many different disciplines. So it requires a tremendous level of depth and breadth, and that is hard to acquire in a short time frame. And I think it gets even more complicated because it's a skill set and there are tool sets that evolve on an almost daily basis. So keeping up with that in itself is a challenge. And I think most importantly, that there is also a divide between what you learn academically and what are the standard tools of the industry. So I think we were talking about this earlier, and one of the things that I've noticed is that when we get students or interns, we notice they are very good at the technical aspects of work in terms of machine learning or data engineering, whatever it may be. However, standard industry tools like Git branching, functioning within the cloud, within a cloud environment. These are things that are standard across the industry, but they are not standard in academic curriculum. So no matter what you do, when you come from academia into industry, there's this steep learning curve. So that's probably where there's a gap, and that needs to be bridged. And I have to say this. I think in the industry, we have to be a little bit more realistic in terms of what we expect. Because take, for example, a simple data science opening advertisement, right? Ostensibly, it's for a data scientist. But if you take a closer look at the description, it's expecting the incumbent to have expertise in data science, data engineering, data architecture, agile methodology, project management, ML ops, domain knowledge. The list is, it's a wish list at the point. It's no longer a role. And that's part of the reason why it's so hard to hire. Because if the industry experts were to be a little bit more realistic in terms of who they wanted to hire, they would hire a team. I understand it's very difficult to hire these profiles, but you would have to build that team slowly, gradually, to get to that point. And I think the way that education can help is by ramping up to include these industry tools.
Yeah, maybe to add to that list, the things that I noticed that cause this learning curve, you mentioned, okay, the Git, Git and any source code management system. I found also, okay, yeah, working in the cloud nowadays is especially relevant because it's almost guaranteed you're going to do that, and it is a learning curve. And then personally, I had to learn a lot about different databases when I started working in industry, because that's not something I really worked with during research. And so, and now at this point, I'm like, oh, I'm kind of a database power user, because if you work in machine learning, applied machine learning, you end up, you're using databases like all the time. But when I started, I wasn't, I didn't even do an engineering degree. I'd taken like math and computer science, and I skipped the database class. So when I started working, I was like, okay, I have to learn a lot of stuff. So like SQL databases, NoSQL, like how they work, all of that. That was kind of a big learning curve. And on top of that, there's like the GUI tools that software developers and engineers use to interact with those databases. And then testing tools, and so on. So I don't know if you guys have other some of these technologies that you learn, when you're working.
Well, I mean, it's so I think it's all about experience at this stage. Like I think a diploma is really good. It gives you a really big footing and knowledge base. But after that, it becomes like mostly like experience, and you have to learn those tools. The same story as for an engineer, probably not what you studied in, and then you end up in a new field, and then you start learning about that field. What I can maybe describe like a little bit the timeline of a project. Usually there's contact with clients, And after this, there's a development of a relationship, and there's a lot of meetings involved in that and understanding the business use case. So that's usually done more like a project manager level. And after when that's understood, then there's a lot of discussion about the data. Then there's some contract being signed and so on. So when you're at that stage, contract has been signed, then you start waiting for the data. So then you have to do a lot of education of what data is needed and how you should suggest how it's formatted and how you will be able to use it. And after this, then it goes to the POC, which becomes the job of the POC, I guess the POC of the machine learning part. That's the data scientist. So I mean, at this stage, like the project management, it was the key to get there. After this, it's an iteration through the model and then reviewing the model by the AI lead, and really figuring out, okay, well, do we really need that feature? Let's try 5 other models to see, first we have the right architecture, or we have the right features. Let's try this type of pre-processing, and then that becomes like an iterative project. Then project manager has to discuss with the clients multiple times, and there's this loop that goes on. So I think it's just a matter of experience and kind of not fearing going in that field. I mean, at the beginning, you're like, what's AI? But it's just a module. It's just like an algorithm that has a different twist on how you build it or train it. That's the kind of the subtlety there.
So yeah, I think right with the gap we have from school and polytechnic and industry, this gap is clear. But when we go at Gaia, there is we do our best to get youth in our team as for training our migrants program and managing a lot of students there, and this is how we want to make this youth exposed to our technology. I think it's one of our people allow them to come to us and work with us. We're putting a lot of people, or I'm putting a lot of people, myself, and putting a lot of people who bring those with talent, because not everybody, excuse me, we can see some good talents around, but in taking here, I'm putting my best to attract them, and I think this is how we're going to have a very good environment. Montreal, especially, is very attractive.
I think you opened the door for us to add and see, right? Very much open in your room, so it's about industry and academic collaboration. Tell us your partners how they could bring that, and so let us learn from each other. Yeah.
I don't know how to tell them horror stories, learning stories, and it, goes on to the Patrick's point of experience. When you come out of school, you have not seen your own work being used, for 6 months, right? Or at least it's rare, right? It happens sometimes, but it's rare that you'll see your own research or see your own code being run for months on end, right? So that's just an experience thing, right? What I've seen often happens in terms of academia industry collaborations is that the people on the industrial side and the academia side are given more or less the same goal, the same requirement, and at least I've seen it happen a couple of times, where there's this kind of assumption that academia will develop a better solution that will be available one day, right? And then what happens is then the engineers in the company, they have to build the thing for their next sprint, and then so they go very iteratively. They build something that works barely, but it works. And then at one point, maybe like 1 month, 2 months down the line, because they have something that's working, requirements and goals on the industry side start to shift. And then the people on the academia side, they're still developing the same model, right? They're still working on the big score, right? And then after enough months, you have this divergence of requirements where even if on the academia side, after like 4 or 5 months, you're like, oh my God, we have this amazing paper and this amazing model that does some really cool stuff. Then the project manager, the engineers on the other side will be like, well, we have something that kind of works right now, and like it would be too costly for us to switch it. And now we're given new features by the user and whatever. So that's something I've seen that.
Like different priorities.
Yeah, the priorities shift with time and they shift faster on the industry side. What helps is if there's a really strong like put from one side to the other, or like if like you know, some of the engineers on the industry side take time to monitor and help, you know, the development of the machine learning stuff, or vice versa. If like, you know, say the students or the researchers are acting also as interns in, you know, the industry side. So that usually helps because it
Yeah, it brings the perspective from the others.
yeah.
Yeah, I'd say, I mean, the challenge in industry is that there's those papers, like I said, based on those very clear data set that everyone uses, been using for so long. But the reality is in industry, you probably have to push the state of the art by quite a lot. And not only that, but you need to sometimes combine multiple previous state of the art into something that works together, like more like a pipeline, for example, for different defect detection, or whatever it's cable in the oil industry and so on. You really need to innovate basically. And for a lot of them, it's rare that you just go on GitHub and like it takes, I don't know, YOLO V5 and just run it and then you have those results. The reality is that you'll probably won't have enough data, so you need to train on very sparse data set. And you won't have enough annotations. You need to maybe do auto annotation, things like that. You don't have the resource to like send it because it's very sensitive data, say, in defense and so on. So basically, you need to push the state of the art every time, which makes it kind of, I guess, a research project in a way, a research and development project. So that's really the R&D, like literally. So.
Yeah, I think along the academy will not go well because we need to find this link with the technical. Because on the technical, we still have a lot of data, but we don't even know what to say useful when what we use is to go into the data, look at the data. That's kind of the data is also the issue. But I believe that the collaboration we have never now with universities in Montreal are very fruitful. I can see from the result I have many patterns coming out, many publications. And also we try to see the understanding, making them to start that because the academic software as a limitation of the machine learning model is not coming to a framework or a system for a system that works. We want to break the machine learning into this part, and it requires some expertise, some knowledge, and some step back, right? Because it won't work in the lab very nicely. That as soon as we deploy a model, it's just it. I think there's a lot of working on, there's a lot of collaboration, step back, and testing strategy also. One of the key problems we face with machine learning is how we evaluate our machine learning. And the student and colleagues, a lot of tools, mathematics tools, and I think it's the baseline of the machine learning, mathematics background, software development adaptation of how we deliver. This is how I see the future. Thanks.
We approach the topic of industry academia collaboration a little bit differently at the bank. We have a dedicated research hub, and what we do is invite advanced students to work on projects that we either think are of interest in the future. So we usually try to identify something that we can put in production 6 months from now, for example. That would benefit not just our team, but the whole bank. An example would be looking at data security. Is there a way that we can secure this data? Is there an automatic way that we could do? So a project like that starts out with our researchers, but we also dedicate some resources from our deployment team. So there are members of our deployment and engineering team that partner with these researchers right from the initial phases of the project, so that we know whether there's potential to put this project into production, and we are able to get funding for it, right? So we actually make sure that at every sprint, we check to see where we are, and then we see if it is feasible, and if it is, then we apply for project funding, and it actually goes to production. So I think we've had some very good results coming out of these research projects, and we plan to expand into those capabilities.
Excellent. So we need some lighter is following along the way to bridge the gap.
If I can add something from like, let's say the other side is, once you're a machine learning developer or AI developer, then one of the advantages, I guess, of, academia, working as hard as they are right now is that I just have to do a bit of survey every now and then find the next, like, the hottest thing and see if there's like code for it. And then it's very easy for me to like test things out if the code is there. So I mean, most of you have probably heard of like, say, Hugging Face transformers, or even good old scikit-learn, all of that. Like the fact that there's these tools coming out of open source and academia, it's kind of like, oh, I don't even start with the goal in mind. I see a new tool that I know I can apply to some problems, and that's really good, So if you're like doing research and publishing your code is always super good, because it, augments like 1,000-fold the chances that anyone's going to use your work stream. So that's on the positive side, So if you publish something that's cool and you publish your code, odds are that someone like me may just find your GitHub repo, clone it and try it out. That has happened a few times.
Okay, good. So I think we can take a step back, talking about like establishing the connection. Like, how do you find students from academia? For us, we love to have like collaboration with people in industry, but it's hard to find a good match. But there are programs out there basically trying to mediate in between. But what is your take on this? How can we improve this? How can we like know each other better?
I think this is one of the stories. We have a data science and engineering division program, which is pretty well known. It is hard to get into, but we have very, very good students there. We also go to events that are organized by Vado, Concordia. I think there's quite a bit of presence. That's actually one of the ways that we engage students. Other than that, I think it's just basically you're at any event, and if you can find somebody from the industry that interests you, you approach them and see if there is an opportunity.
Yeah, I think coming to collaboration with university and school, I think Ericsson has a lot of experience with that. I think we are pushing, we're still pushing. We have MyCast program. We have 6 cluster in our Gaia with 42 projects, around 10 to 1 university across Canada. I think we are doing a lot in this direction. Yeah, we also try to attract students in our group for interns. I was here last month, I think, for the job fair to look at people here, and this is, I think, it's the direction to go.
I think it's interesting because so you're working at National Bank and Ericsson, and these are like really big companies where there's a lot of experienced people. You already have, your data science experts and senior people, and they can do a very good job of coaching students and interns. However, for example, now I'm working at basically a pre-Series A startup, and in that context, it's much more difficult. And that's that's where a lot is expected, you know, from students and interns. And if like I couldn't imagine hiring someone who hasn't had like some internships in like companies, right? I couldn't imagine hiring someone that only has research experience, because the hill is going to be really tough to climb. And I just say this because it's in the context of a startup, you know, so we don't have tons of money, we don't have tons of people, and people need to be very, develop many skills at once. And especially if you're working remote, you know, that's even worse. So I feel like the bar is higher when you have less resources and less people.
Yeah, I guess personally, we're also a startup, and I mean, we had a really amazing intern that came for the summer, and that became like full-term employees, and to me, like it's just through programs like MyTac and University Sherbrooke and Concordia and so on. But I think the key is like you need kind of a little bit of applied AI or applied need some kind of a little bit of industrial background. But it does take some energy to bring someone to a certain place. But usually if you have that industrial background from those projects, and depending on people's skills, it usually goes really well. And we have interns that I think they've been with us for 2 years, and like amazing, like, you know, so that's one thing. And I'd say for developing that relationship between academia and, at least for us, is that we have tools to test the model robustness. And I mean, we're considering like kind of making it more available, especially for researchers to use them, so that they can really understand the parameters of how do you test AI models. So I mean, for us, because to industrialize AI, there's a big hill. And I think if we're not careful, I don't want us to fall in another AI winter. And we do have a big challenge there. And but when I look at the market and how much money is being invested in AI, it's really great to see. But also, when I look also at how much interest and also the power of AI, I mean, if you have one good model that's robust, if you copy that, then you just keep copying it, using it in parallel. The scale of what you can do is like it's really large. So I mean, AI does have an incredible power, more than so many other technologies, and the way it's moving, like when you go to NeurIPS and CVPR is just AI. NeurIPS is like this, it's still too small, you know. I mean, it's even hard to get tickets there. So I mean, how fast it's growing is probably faster than any other technology ever. So yeah.
So thank you. I think we're almost at the time. Any last questions? Excellent. So I want to thank you all for your insightful comments, for coming here, and wish you all like the best in your AI and ML engineering journey. Thank you. Thank you.
Ah ouais, je suis pas tellement.
Meeting you.
Great. But what is this? I'm super intrigued. Like, oh, okay, it's a mug. And I see. Okay. Great job.
Okay, let's have maybe a sort of conversation about
Without any company, like distribution, what you need to. I didn't. Like, okay,
Yeah, yeah.
I want to
yeah, absolutely. Yeah. What exactly?
maybe I'll just put you back as Okay, hello, I think we can.
We should start. Okay. Please, ask the comment. Okay, so I think we start anyway. So this is the last session of our morning session. Okay. So I'll introduce Mike Raba. So Mike Raba is a research scientist and manager in FAIR, so which is the fundamental AI research group of Meta platforms. And he was a professor at McGill University before joining FAIR, and his research interests for machine learning, large-scale and distributed optimization, and federated learning. Thank you, Mike.
Thank you, Hank. It's working well. Can you hear me okay? No? No? Now? Oh, a little bit now? Okay. Let me know if not, I can something next. So yeah, thank you everyone. Thanks to the organizers for the invitation, the opportunity to speak here today. Excited to tell you about this work on asynchronous federated learning at scale. Clearly, this is work that was done with a lot of collaborators, so I wanted to just provide a list of many of the collaborators who are all at Meta. And in particular, I'd like to call out the first three on the left, Dimitri, no, they're mixed up. So Dimitri Shittes, who is second down there, and John Nguyen, who were three of, among all of the group, I mean, everybody was a significant contributor, but Dimitri Shittes and John were really doing a lot of driving of this project and did a lot of great work. So I'm going to be talking about federated learning and federated optimization, and want to give a quick overview so that we're all on the same page. So in federated training, the idea is we're going to do large-scale training of a machine learning model, and this is different from other typical large-scale training that you might have encountered in the past. So we're not just training in a data center. You don't have access to all of the data centrally. Really, the promise of federated learning is that we can train models without the data going into the cloud. So we're actually going to be training models on device, as pictured in the bottom corner here. The data never leaves the devices, and so we're going to be coordinating across many devices, say on the order of potentially hundreds of millions concurrently, coordinating with servers in the cloud in order to perform this training. And the motivation to do this is really privacy. Users don't want to necessarily have to upload their data into the cloud. And so this privacy is one of the things that makes federated learning both very interesting and at the same time challenging, especially compared to other large-scale distributed training tasks. And just for example, normally if we have all the data in the cloud, then we'll shuffle the data so that it appears roughly IID as we're training, as we're going, doing epochs over the data set. But if we can't get the data into the cloud, we can't shuffle. We can shuffle on a device, but we can't necessarily shuffle across devices. And you might imagine that different devices are going to be producing, data with a slightly different distribution, right? This data is coming from users who might be either using a certain feature or an application in different ways or to different extents. And so we can't necessarily commute the data across the workers to get IID subsets for training, validation, and tests. We also don't want to communicate transparently between users directly or between users in the cloud. And that's because, well, for one, we want to keep the data private. And for two, it's been shown in previous work that if you communicate things like a gradient or a model update, that can also leak unintended information about the data. And so this is just an example from this paper listed here by Guy-Ping et al., where on the left, you see one of the original images that was in the training data set. And on the right, you see what you can recover if you perform an attack just by observing gradients that are being communicated back and forth. So in order to avoid having these kinds of reconstruction attacks, if we want to keep user data private, usually the solution is going to involve combining a few different technologies that are listed at the bottom of the slide here. The first is secure aggregation, which is going to use some sort of cryptographic techniques so that we never see data or a gradient update for any individual user. We only see things in aggregate from several users. This helps provide some protection. And the second technology that we'll typically incorporate is something called differential privacy. You can think of this as adding noise or perturbing either your gradients or other messages that you're sending in order to add some protection to it. This makes it harder to do these kinds of reconstruction attacks. So, as we mentioned, so a key difference in federated optimization is the fact that we want to keep privacy or maintain privacy while we're training. We'll use those privacy enhancing technologies that I mentioned previously, in addition to not being able to commute, so we have to deal with not necessarily independent and identically distributed data while we're training. And in addition to these challenges around not having transparent communications, there are other challenges that come up. Things like data imbalance, different users using features to different extents. And so some users might have much more data than others. Heterogeneity, I kind of already mentioned, the distribution of different users might not be the same. Device availability is also a big one. So we want to do this training without impacting the experience of the end user. And so that means usually we're going to train when certain criteria are satisfied, including the device not being used for other purposes. So it's in the background. But you never know when the user is going to resume using their device, in which case we need to stop training right away. And so you might see devices drop out unexpectedly in the middle of training. And there's others that I list here at the bottom. And so, yes, so these are some of the challenges that differentiate, in my view, federated optimization or federated training from typical training in the data center. So let me step you through. I'm going to be talking about asynchronous federated training as a way to speed up and also maintain security in federated learning. But first, let me show you kind of what's the standard synchronous approach that has been used in the past. So in this case, we have clients, mobile devices on the left. We have a server in the cloud that's coordinating this training. And so clients are going to indicate when they're ready to participate. They're in the background, their devices are plugged in, so we're not going to use up their battery power. They're on Wi-Fi, so we're not going to use up their cellular data plan, things like that. Then the server in a synchronous round is going to send the latest copy of the model that it's maintaining to a bunch of different clients, all the clients that are in the cohort that's participating in that round. Locally on device, the clients are going to receive this model from the server. They're going to perform several updates locally on their data, updates like stochastic gradient descent, essentially trying to say, okay, how would I improve this model just based on my own data if I wanted to make better predictions on my local data? Once all the clients finish performing those updates, we're going to do some secure aggregation. So this is where we're going to aggregate these model updates back at the server. I'll describe secure aggregation in a little bit more detail in the next couple of slides, but in a nutshell, the secure aggregation ensures that the server only sees the aggregated update from several clients, not any individual client's updates. And then the server can use that model, that aggregated model difference in order to update its own model, and we'll repeat this process. So what is secure aggregation at a very high level, in secure aggregation 101 in like 1 or 2 slides? Well, we'll think of this as basically a black box like this dotted box here, where the clients are going to be performing some protocol. Typically it's a cryptographic protocol, where from their perception, they participate in the protocol, they send some messages, and they each have their own model update, this delta. And what comes out of the box at the other end is the sum of these model updates, perhaps plus some differentially privacy noise. And so the important points are that the server is going to be at the receiving end of this box. It's going to see the aggregated update. Perhaps the clients might also get the aggregated updates, maybe not, depends on the protocol. But at the end of the day, the clients only ever send messages in a way that nobody gets to see their individual updates. Okay, and so I'm referencing at the bottom of the slide one paper that first described how we might do this in a federated context in 2017. So this was from Bonowitz et al. And just in a little bit more detail, how they go about accomplishing this is the following. So conceptually, you think of having your end clients that are participating in this round, shown at the left of the screen, and each client is going to generate a random message, MIJ, that it sends. If it's client I, it sends that message to client J. That's a random number. Now, the secure multi-party computation protocols operate over what's called a finite field. So we're doing integer addition with wraparound, essentially. So if we overflow, we're just going to wrap around and keep on computing in either direction. And the idea is the following. So every client sends these secret messages to all of the other clients. And what each client is going to send now to the server is the sum of its original message delta I plus all these secret random numbers that it received from all the other clients. And those secret random numbers have the effect of essentially masking whatever the message was that client I was going to send to the server. That's great. But how do we get out what we want at the end of the day? Well, the key thing is that when we're sending these secret messages to all of the other clients, we design them in such a way such that everything cancels out, right? So that when the receiver, so in the cloud in this case, when they add up all the messages they receive from all of the different clients, the sum of all those MIJ parts adds up to 0. Makes sense? And so what they're left with is just the sum of the deltas. This is, again, at a very high level, how this works. There's a lot of details that go into making it work correctly, which is just to get an idea of what's going on. So you can imagine, in order to run a protocol like this, we need to, it might be a little bit challenging if the number n of nodes participating in this synchronous round is large, then, well, the number of messages that need to be sent back and forth is on the order of n squared. Subsequent work building upon this protocol has improved this from an m squared type of communication overhead down to an m log m communication overhead. And there's been other improvements, but at the end of the day, this still requires a lot of messaging, potentially between clients, as well as waiting for all of the clients to be ready before we can proceed. Okay, so let's take back and do a reality check for a moment. So I already mentioned this first point, which is that typically, well, I didn't mention it exactly, but typically in machine learning, when we're training a model, we think of representing the weights and the biases of the model as floating point numbers. Whereas secure multi-party computation, secure aggregation protocol I was just describing, those operate over integers or finite fields. So there's a little bit of a mismatch, but we know that we can do things like round, quantize, do this carefully, and typically cross our fingers, things will work out okay. We're also training with stochastic gradient descent. That kind of rounding, is kind of like an additional noise, but for the most part, we know how to do it. The second point is clients are mobile devices and they can only communicate through the server. It's really impractical, or so far it has not been practically demonstrated that you can coordinate this direct messaging between lots of clients at scale. And to give you an idea, the number of clients that might participate in one round of this protocol that we would need to coordinate amongst might be anywhere from 1,000 to 10,000. So it could be quite large. So all the communication is going through the server, which means the server sees all of these messages. So we typically say we're operating in a model where we trust the server to be honest. It's going to do what it says. It's not going to memorize any of those individual messages. But of course, and the Fourier server would have all the information that it needs in order to be able to basically subtract off those secrets and recover the data of any individual client, which is not ideal. The third part, which is actually complicating things, is that clients are flaky, like I mentioned. They might drop out unexpectedly in the middle of a round. They might have said, hey, I'm ready to go. You get the message, and then all of a sudden you never hear from them again because the user unplugged the phone and started using it to do something, and so we have to stop training. And because they drop out, if they drop out midway through the protocol, if they send some secret messages to other peers, and those peers include that, but then the server doesn't get all the information that it needs to cancel all that out, the server is going to end up essentially with a noise update, which is not ideal. And so actually a lot of the work that goes into those papers that I mentioned is very, very clever ways of trying to figure out how to deal with clients that drop out in the middle of a round. But it makes it complicated to run this protocol. The last point is that we know that federated training is one form of training in machine learning, and typically our machine learning training methods like stochastic gradient descent or whatever optimizer or Fisher optimizer you want to use, these are iterative methods. And the speed at which we can train a model depends on how quickly we can take a step. And so in this context, that means how quickly can we complete one round to update the model at the server. So having low latency is key here. So having to wait for all the secret messaging to occur and then aggregate everything to the client, that's one aspect that slows things down. But just to show you in pictures also what can happen, and actually what typically happens is, if we look at over time, each client is going to download the latest copy of the model at some point in time. Different clients have different upload and download speeds and different processing capabilities. And so it might take them different amounts of time to download. It might also take them significantly different amounts of time to compute what they would like to update the model to based on their local data. That's the compute part of things. And because this is a synchronous protocol, we can't get started until the last client finishes its computation. Then we can do the aggregation. So you can see this leads to lots of idle time or dead time, where there are clients who would be otherwise ready because they finished their compute, but they have to wait for the slowest node or the straggler. Yeah. And indeed, this what I was showing you on the previous slide is not just some hypothetical situation. We actually see this in practice. And so this is data from training a model on the order of 100 million clients, so Android devices. And what I'm showing in this histogram is the density of the client execution time. So the time it takes for a client to download, perform their updates, and say that they're ready to go to do aggregation. And so the first thing I want to point out here is you can see it is pretty peaked to the left. Left is good, that means fast times. But I want to point out that the x-axis here is on a logarithmic scale in seconds. And so this might take anywhere from, on the order of 1 second up to a few hundred seconds. And so if we're waiting for the average client, you see that's in the middle there, that's the mean execution time. Sorry, that's the mean execution time for a single client, right? But typically we need to wait for on the order of 1,000 or maybe 10,000 clients to complete the round. And so we're off in this upper quartile or percentile for this mean round duration, which is always going to be quite slow, right? On the order of hundreds of seconds to complete one update at the server. And we're going to want to do perhaps thousands or tens of thousands of those updates. And so this process can take really a long time. Of course, we know there's going to be some trade-off. We want to provide privacy and security. That's not necessarily going to come for free. But we would like to be able to do that and do it faster. And that's what we've been working on with this asynchronous protocol that I'll tell you about next. So before I tell you about our asynchronous protocol, let me tell you about how the synchronous setup has been dealing with stragglers, with the slow nodes. That's been by essentially fixing a target time and saying, okay, we have until this deadline to finish our computation and report back to the server that you're ready to go. And so that means one of two things is going to happen. The client that was taking a long time to do its computation is either going to have to stop its computation intermediately if it can and use this partial computation. Maybe instead of performing 100 local steps or 100 local updates, it's only going to perform half. Maybe it's only going to look at a fraction of its local data, which might not be ideal. Or we're just going to have to exclude that client altogether. But either of these things essentially means that we're not using all of the data that we could have from all of the clients. Okay, but this is also going to allow us to speed things up significantly because instead of having to wait for 100 seconds per round, maybe we can set our threshold at 5 seconds or 10 seconds, and that'll give us a very non-trivial speed up, right? Even if we cut it in half to 50 seconds, that can make a big difference. This has interesting and perhaps surprising, perhaps not surprising consequences, but it has very concrete consequences because clients are different in wonderful and interesting ways. Let me just tell you what I mean by that. So just in numbers, for a task, the task of showing you the data point before is training a simple language model, the kind of model that your smart keyboard uses to predict what word you might be typing next. And so perplexity is the measure that we use, the metric that we use in this case, and lower is better. Lower means we have more confidence about what the next word might be. And so if we were to use that basic FL where we just take all the users, but we are as slow as the slowest straggler, then the time to train this model to our desired criteria was 130 hours. That's several days. The average perplexity across the entire population, once we do that, was 68. Okay. And maybe the interesting thing to note is that, as I mentioned before, there's a lot of data imbalance in these applications. Some clients have a lot more data than others. And so if we look at the clients that have the more data, the 25th percentile, or even the top 1% of clients who have the most data, then we see actually the perplexity goes even lower on those clients. It's not surprising. They have more data. And so if we use all that data when we're training the model, then the model is also going to make better predictions for those users. On the other hand, once we impose the timeout, we can train much, much faster, right, in 19 hours. So cut this down from several days to 1 day, but we take a hit in terms of the quality of predictions that the model is making, right? First of all, the average jumps up from 68 to 73. It's noticeable. If you were to start using this model, you would be able to tell the predictions are not as good. They're still not bad. But maybe the more marked thing to notice is that, especially for those users, those devices that had a lot of data locally, the predictions degrade severely for them. And this is kind of undesirable. We'd like to avoid this as well. So can we both speed things up and also have better quality models? That's kind of what we were going for in this work. So in brief, the asynchronous federated learning protocol that we're proposing in this work operates roughly as follows. So we're going to have clients that are proceeding, and we're going to set a threshold not on the time, but on the number of client responses that we need to receive before we perform an update at the server. Okay, and so in this cartoon example, I have maybe 4 clients that are always computing, but as soon as I get 3 updates, I'm going to go ahead and update my model at the server and move on to the next version of my model. And importantly, because it's asynchronous, I'm going to let clients like client 2, who might take a little bit longer to do the computation, I'm not going to cut them off and say, hey, I'm just going to throw away your update, or I'm going to use the partial update. I'm going to let them keep on going, and they're going to send me their update at a later point in time when they're ready. Okay. And at the same time, I'm going to start having some other clients download and compute and perform updates. Does this make sense? Okay. So this is great conceptually, and this is pretty obvious why this is going to speed up training. But the big question, the technical challenge that we had to deal with in this work was, how do we make this work and still use some sort of secure aggregation protocol? How do we still ensure that the server never sees updates from any individual client? And so there we used something a little bit differently. So clients, again, this is just describing the protocol in words. Clients potentially started computing from different models. This is something else we'll deal with. I'll actually put back up one slide. You'll see at this later point in time when we perform an update to get model version 2 or at step 2, these clients started computing their gradients or their updates based on this new model M1, but the response from client 2 was actually based on an old model. It's stale by 1 step in time, right? And you can imagine, what does this mean? Well, it means the model moved, but we're using a gradient from this old point in time. We have to be a little bit careful about that, because it's not totally obvious that this old gradient or stale gradient is still pointing in a useful direction to tell us how to update the model that's even here in that interface. And 1 step might not be bad, but you can imagine staleness might grow to much higher than just 1 step. And so what this first point here is saying is that late updates are still valuable, but perhaps we want to downweight based on how old they are. If your update is very, very old, then maybe it's not as useful to a step. We're going to aggregate the responses from clients in a secure buffer, and we only want to release that. So this is the main concept here. We're going to aggregate the clients in a secure buffer, their responses. We only want to release an unencrypted version from that secure buffer to the server to update its own model once enough responses have been received, once we reach that threshold, 3 slide. And so the big question is, how do we implement a secure buffer, right? And so at a very high level, the way we've proposed to do it in this work is using a special type of hardware, secure processor that's called a trusted execution environment, or you might have heard of it also called a secure enclave. What this is it's a secure area within the main processor, which guarantees confidentiality and integrity against the host operating system. So even if you're a sysadmin logged into the operating system of that server, everything that's happening in the trusted execution environment is encrypted. So you can't actually read that memory and see what the values are that were received from those other clients, right? So like the way my colleagues like to say is, what happens in the trusted execution environment stays in the trusted execution environment until it decides to release that to the server. And this is not a fictional concept. There's several companies that manufacture devices. Intel has their SGX, ARM has something called the Trust Zone, AMD has something they call SEV. So you can buy processors that are equipped with these. You can also get access to processors with the secure enclaves in the cloud. So this is how we're going to do secure aggregation and have our secure buffer. And it turns out that this makes a very non-trivial difference in the performance of things. And so if we were using FL federated learning with that timeout, before we saw that we could reduce the time significantly, but we take a hit in terms of the performance, especially for those users with lots of data. When we use this federated learning with the buffered asynchronous aggregation, FedBuff for short, we can reduce the time even further. And at the same time, we get better performance across the board. And importantly, those users with more data are no longer seeing a reversion to the mean of the distribution. They're actually seeing that performance benefit you would expect to see. You might be wondering, how did we actually get both faster and even better performance? And in this case, we're able to get our per step time, our per update time at the server to be so much faster that we can even take more steps in those 18 hours than either of the two previous approaches were able to take. So we're essentially training for longer, but in less time. Okay. How do we do this at a very high level? How do we implement a system like this? If I would quickly cover the system design. So there's these three principles are really the key things to make building an asynchronous server at this scale feasible. So the first thing is, because we're asynchronous, and the whole point of being asynchronous was not to group clients together into cohorts and create dependencies among the clients, but we try to design the system so that there's no dependence between clients. So we have clients in a client pool that get matched with a selector. The selector is basically saying, okay, you're ready to go and you've got the right data for this task, and I need a new client right now, so let's start processing. There's a lightweight coordinator that's coordinating everything here, the aggregator, and then the trusted secure aggregator are the ones doing the aggregation. In particular, the trusted secure aggregator is what's running on that secure enclave, on the trusted execution environment. And so, like I already mentioned, having no dependence between clients is one key thing to make sure that we can proceed asynchronously. So if one client drops out, it doesn't affect the other clients that are currently computing. But the other thing is we want fast client replacement. So as soon as one client finishes processing, either it completes its round or it drops out, it doesn't respond to our heartbeat, our ping. We want to be able to quickly replace that client so that we can keep the level of concurrency, the number of clients that are concurrently processing, keep that roughly constant over time. The third thing is that we need to be able to perform these updates quickly once clients have finished. And so that's why we need this fast model aggregation. In fact, doing the aggregation on this trusted secure aggregator in some ways allows us to do this because it forces us to make the operations running in that secure aggregator very lightweight and only essentially doing the aggregation. So we can do that quickly and move on to the next round. Good. So let me wrap up, and I wanted to be mindful of time. I don't know if I was too short or too long. I hope I'm okay. That's good. So just to wrap up, summary of what we talked about today was asynchronous federated learning. We saw that heterogeneity gives rise to very real challenges in federated learning, especially at scale. How we deal with it has some implications, right? So timeouts for those slow users also impacted the quality of our model. We've seen heterogeneity and other work also have an impact. And so one example of that is, different devices might also have different processing and memory capabilities. And one earlier practice in the literature was essentially to say, well, we're going to limit our training just to those newer devices that have enough memory to actually fit the model. But what we've seen in other work is that can also essentially impact the quality of predictions made by that model on users that have older devices. Even if they can't train, maybe they can do inference with the model, but it's not necessarily going to be doing as well as what you would like. And there's ways around that. We also talked about this asynchronous secure aggregation. And I mentioned the implementation that we proposed in the paper using a trusted execution environment, using secure hardware. Shortly after we posted our preprint online on arXiv, there was a group based out of the University of Southern California, so Ali Buller and Estemer, who proposed an alternative cryptographic protocol similar to the one of Bonomit's that I mentioned earlier, but with some clever additional techniques and tricks, which would allow you to potentially do this kind of asynchronous aggregation using a cryptographic protocol if you don't want to rely on secure hardware. So there's other alternatives, and even since that work, there's been other follow-ups. So if you're interested in more, I would point you to our two papers. FedBuff goes into a bit more of the theory, whereas Papaya really talks about the system and the implementation and the evaluation at scale. And we also have this FL-Sim simulator, which we used to prototype before going off and deploying. So with that, thank you very much for your attention. I'm happy to take questions.
Thank you very interesting talk.
AI,
Maybe next word. And what other applications you can use instead of that method?
So this is like the drawback of working at a company sometimes. I don't know how much I'm able to say.
Okay.
Other than that, there are others, but I think the only one that I'm permitted to talk about publicly is the range modeling at the moment. But there are others. I think you can imagine lots of applications where you would want to run a model on your device. And so in any of those applications, or also where you would want to keep your data private. And so for several of those, we're actively working on using federated learning.
I know that for medical cases, hospital data, we can use federated learning for security, because hospital cannot share the medical data.
That's right. That's another great example. It's a slightly different type of federated learning. But for sure, coordination of training models among hospitals is one. So the type I was talking about today is something called cross-device federated learning, where we're really talking about individual devices. Often the example with hospitals is referred to as cross-silo. So there's some different challenges that come up there. It's each silo being a different hospital. They need to keep their data secure and private. And at the same time, you can imagine in a hospital, they might be able to run this on a server that's always powered and always available. So some of the challenges I talked about go away, but there's still a lot of very serious challenges. And this could be useful there as well. Yeah, thank you.
Thank you so much. You mentioned client's diversity.
Yes.
What was the criteria you used to measure this diversity of the client? Then second, like with the related, now the client has the control over the things of the background. Now, how do you generalize? For example, so many people across certain regions will have different kind of performance. How do you generalize it with different regions? Because some other projects, other factors will account. Yeah, so how do you generalize it?
Yeah. So I think for your first question, how are we quantifying diversity? In the work I was talking about today, the main way that we look at diversity is just in terms of the amount of data that each device has, but you can clearly imagine there's several different ways to go about this, looking at geography or other characteristics. But yeah, what I was talking about today was mainly in terms of the amount of data. Yeah, and the second question, sorry, remind me, the second question was how do we generalize? Yes. Okay. So the numbers I was reporting today also were either average over the entire population or grouped based on the amount of data at each device. I think there's a big literature on various metrics for fairness and ways to think about training models that work well across different subgroups of a population. And I think it could be natural to incorporate those ideas into this type of training, but it'd be a step beyond what we've done so far in this work.
And that was a very nice talk. So I have a question about, you mentioned that the local clients update may be divided down. So does that mean that the global model will perform very differently from client to client?
This is a great question. Yes. So in general, regardless of the three approaches that I mentioned in the talk, synchronous where we use everyone, synchronous where we threshold and discard information or only use partial information for some clients, or asynchronous, they're going to be three different models, and each one is definitely going to perform differently from client to client. And so I think there's several extensions of federated learning beyond what I talked about today, but what we and what many others are actively thinking about and working on deploying to try to improve the performance on each individual, also recognizing that different models are going to perform well at different users. Broadly, this is called personalized federated learning. And so the idea might be, if each client, typically in this case, each client has a relatively small amount of training data, not enough to train its own model from scratch. So there's benefits to pooling across all the clients to learn from each other to some extent. But there's several different ways people talk about trying to personalize the model from there, right? You can imagine you take that as a baseline model and fine tune it locally, or maybe you have part of the model that is shared, the weights are shared across the whole population, and maybe there's only another part of the model that is fine-tuned or trained specifically for that client. I think the community still hasn't reached consensus on what's the best way to do this, but there's lots of proposals. Another proposal is to try to group clients together into clusters of similar users and train a model per cluster. There's interesting but complicated challenges for how do you group clients in a way that preserves their privacy without revealing information to the server about them. So I think there's lots of interesting different ways to go about this, but yeah, personalized federated learning is the general field. I'm happy to share some references to some work we've been doing and others have been doing offline if you're interested in more.
Thank you, Mike. This is Mike Caracol. Okay, that's the end of the morning session, so it's not time for lunch. So afternoon we will contact you. We'll have a very interesting report on AI for the networks.
You don't want to miss the tutorial. Next time, someone else. Yeah, for the screen name up there. The question about this asynchronous tracing. Like follow your just that asynchronous. Yeah, exactly.
Because I don't
I think you can set up this on the chairs. You can see. No need to be, just sit. Then move from time to time if needed. Sure.
Yeah.
Can you join on Zoom?
Oh, I don't know, yeah, it's my computer, it's like, it's not my computer, I have a problem with my computer, I borrow a computer.
Okay.
Repair. I will do something.
对，但是就我们的电脑就后不知道，我等会儿看他们让他们帮忙set up。
Can you enable that? I cannot start video.
Yeah, go and check. I just gave the permission now. Ask to start.
Yeah.
Yeah, so go and check it.
Okay. We will get started.
Yeah.
Welcome back, everyone. I hope you had a good time and that everything went well. Okay. So we are continuing our program with our tutorial. So we have a very interesting tutorial ahead of us. You can see the lineup. So many people. Providing some hints about excellent quality of our tutorial. So maybe just a few words. Why we thought a tutorial was very important for this type of events? It's because I think the core of SEMLA has always been the students. So we think it's very important to stimulate the friend, right? So we have seen panels today on the education, what we need to do to upskill our different programs so that our students are ready for delivering this system that relevant and then they're getting more and more programs in the industry. So this tutorial, unfortunately, is a bit short, but through the tutorial, there will be a lot of material that will be provided for you to kind of continue on this task at home or later on. So the tutorial is mostly on quality assurance. So we'll be discussing testing, okay, using some of the tools that we have been producing through research over the years. So we selected a subset of those tools, and our tutors who graciously agreed to run the show will walk you through those tools, how you can use them to actually improve the quality of your machine learning code. Right? So we'll be testing deep neural networks, especially quick forwards and convolutional learning. So with this, I will give Lei maybe just a brief introduction of the scope, and then we will get into this.
Sure. Try to do a screen or
You can.
try to do a screen or I don't know.
Yeah, you can share.
Okay, yeah, maybe I can share on Zoom. Okay. So
Or just like.
yeah.
What is your?
That's
Okay. Yeah. Okay. Yeah. Thank you for attending the tutorial session. Yeah, it's a great pleasure that we host this tutorial. The title is a little bit big. It's called AI quality assurance, but the content is not that big. We mostly focus on the testing and analysis of neural networks. As was mentioned, we have a couple of tools developed over the past several years, and so today, we want take this opportunity to walk through how to use these tools in the hands-on context, AI tasks like testing the image classification task and also the speech recognition task, so on and so forth. So before that, this is a agenda for today. So time is really tight, actually, considering content, that we have prepared. But for you that may not know the background, so I have a very quick review because the data-driven AI is really important. We have seen a lot of things in the last decades, and but that way the quality is really a big thing. We see a lot of accidents, like these real-world cases in Japan that the perception cars of the Honda that recognize the Japanese noodles brand as the no entrancy. So this is a really interesting thing. But definitely what I want to stress here is the importance of quality and reliability if you look at the market shares on that part. So basically, when we think about developing the high performance or high quality machine learning models, it's actually a very complex task. So after we have that model ready, then the next thing is that how can we step by step walk through this quality by some tools that help us trigger this behaviors inside. So here we mostly consider testing because it's one of the most widely used techniques in quality assurance in the industry. And three key elements I think you should know before walk through the code is first is the test generation. That's if you prepare a set of data or a set of test cases that you trigger and run the system. And you use the oracle that can define in some specific ways, like traditional software, you can use proposition logic assertions. You can assert that kind of properties that satisfy at a particular program state. And another thing is about completeness or of the testing sufficiency that we use test criteria. For example, in traditional software, we can use full coverage, like branch coverage, or this kind of variance of the coverage. So here is a very simplified comparison of these kind of things like the criteria, test generation, test oracle in rule-based software or in deep learning or machine learning. So it's very different if you look at this. So, for example, in deep learning, we don't have a very specific rules that we don't know how to specify good test criteria and how can we perform test generation as we used to do in traditional software, and how can we specify the properties or oracles of the like the neural network. So, for example, cat and dog classification. How can we correctly specify the properties of the cat and dog? So that's the point. And if you don't know much about the testing, this is actually very simplified workflow that we have the source code or software on the task. And our testing tools or tester, the goal is to write another piece of code in terms of unit tests or other integration tests. Then the goal is to run this test on the software on the test. That is your code run test. And then you observe its internal behaviors in Oracle or other techniques for analysis. And to measure the sufficiency of testing, because it integrates. So the code coverage is definitely the most obvious and the simple one. So that's also widely used in industry. So this for traditional software, you can see we here give an example of Jacobo. It's a very, I think it's very useful tool for open source usage. So you can see that the green line are covered by your test cases, red line is not, and yellow is partly covered and partly not because it has multiple branches. And when you have a complete look at this your software test, you can look at the coverage of code at different levels, like in the package, class, function, line, branch, and so on and so forth. So here is a very, very simple example from the Java unit test. So that we prepare some kind of test cases you see at the beginning, and then we assert very general property that whether the object U is equals itself. This is the reflexive property that should be satisfied by all the Java objects in that. So and similarly, because the Taco Parry has a limitation, it's quite shallow. So then the mutation-based analysis is used that we inject the fault by purpose into this original software test. For example, you can change the plus to minus, minus to plus, whatever. So you introduce a fault and you see whether you can use your test cases to detect these kind of changes. And there is also a really nice tool called PyTest there, so you can see that. So I inject all and see whether your test case is covered that or not. Yeah. Okay, so then this basically the content, and yeah, so and in this talk, so we want to mirror this transition software testing pieces, test generation, code coverage, and Oracle. But our goal is to see how can we do that for deep neural network on the AI parts. And yeah, then we will walk through a little bit of these several tools. First, we'll start with full concept on the testing generation, and then we will go through like the basics of the neural coverage. That's what we actually recognize as so far in the neural network testing, and then we go through another tool like deep stylized to a more advanced speech recognition tasks. So yeah, and then we will forward this to our This is
Okay, so thanks, Nick, for the introduction. And now we'll move to the first piece. So we have three pieces in the tutorial. I strongly encourage you to follow the tutorial. Subscribe tonight, so we'll try yourself as there will be the downtime. And even if you don't finish it here, you will be able to continue afterwards. The goal is really for you to grasp how you use this tool, in which use cases they can be useful for you, and so you can keep on the learning. So start of the first piece, and then move. Okay. And if you have any questions, so it's a tutorial. Just feel free to ask the questions. It's not one-way interaction.
The code and the environment is already set up. So if you want to do a hands-on, then you can follow this and just on your computer.
So I just push it online. So just if you Google SEMLA 2022 on GitHub, it will be the first one. So simple way to share the link. So I will open. It's really hands-on. So just it's an application of how to do unit tests for a CNN model. So I will go over the structure here. I have some batch samples that are NumPy arrays that are zipped, and they contain like 32 images here by a batch. We have 20 here from CIFAR 100 dataset. We have a model which is an efficient net trained on the CIFAR 100 to classify those images, and it's a hash 5, so it's a developed in Keras. And the idea here is to do a black box testing of this CNN. And
I think maybe it's not.
Maybe you want.
Yeah, just use them.
so I will just repeat that we have CIFAR 100. This is the 20 batches of 32 images, and they are zipped. And we have a model which is an efficient net trained and optimized on CIFAR 100. And we will build tests to test this model in a black box way. And the idea to build, it's a unit test. But first, I will go over the helpers I prepared. And this is a wrapper. So I will wrap this model. So I will load this model from a path. I will instantiate the feature engineering if I have, for example, a normalization or a step to prepare the input before doing the inference. And we have the batch size, and load and predict will be the abstract. And I will implement this abstraction using a TensorFlow API to load my hash 5 model, which is written in TensorFlow, and do the prediction. Prediction will return the classes. We have batches of 32, so we have 32 classes here. It's a list, and probability will be a matrix of 32 and rows, and each row will be the probability of each class, which are 100 in the CIFAR dataset. So this is just the wrapper I prepared to handle the hash5 model and do the prediction using it. Transformations, this for the exercises, I will have just transformation of image. We'll use that to generate our test. So I will start. So here, as any unit test, I think for Python, we create our test case. So here we create a random test, and this is the first test suite I will create will be a random testing. So here we just have three methods. So I will just write the test robustness against white noise, and after that, I plan just the exercise will be to add test robustness against rotation, against translation, and all the transformations is already provided. But the idea is to how to test randomly the robustness of a neural network. And we have the setup and the tear down function. Like in the setup for testing the CNN, I prepare that we load the data here, we load the model, and we will predict all the predictions of on the original data set we have. So we have a bunch of data set, we collect here the prediction and we set it in the class. I will show you just the class of a batch. So I represent just we will the light. It will be there.
Turn off.
Is that okay to turn off?
Yeah. That's what we want to do.
this. So
Yeah, it's like a movie.
okay. This sounds good.
No, yeah, just
Yes. So the idea here is I want just to show you the class batch here. So I will have the inputs. So this is the batch of data we have. We have the labels, which is the ground truth, and I will add the predictions and the probabilities of the original model under test for this data set. And I will explain why we prepare this. So first, my setup. So the setup function in unit test will be executed before all the tested. And this idea is I load my data set here, I load my model and under test, and I will run my prediction over all the original batches I have, and I will set these predictions and probability. So I have this batch class I showed before, and this one contains the inputs, the labels, and the predictions. So now I will fix some parameters. So how much repeats I have, how much samples I use, so how much batch data I will sample to do the test, how much repeats. So I will transform this data set 3 times, and I will check the robustness of my model. And here I have the delta, so how much perturbation I allow in the image. So the image is normalized between 0 and 10, so it's the kind of 1% change here. And I have mutation probability, so how much the ratio 1 is 100% of the image, and 0.1, it's like I will touch 10% of the pixels, and I have the right to do a delta on it. So 1% change in 10% of the pixels in one image. So the max tolerance, how much tolerance I allow in the degradation. So it's a kind of failure rate. I allow 20% maximum of failure rate when I do this kind of transformation. So the tear down just will free my memory and will free the base test data and the model under test. So now we have this method. So this is the unit test robustness against white noise. So we prepare the failure rates we have. So we will go over how much sample we have. So I will do here a random choice. I have the base data, which is a list of the batches I load. So I will choose a batch randomly. I have its shape. I have the size of batch size, or how much input I have here. So the idea here is to generate a random, like a uniform vector between 0 and 1 of my size of the input. And I will do 2 times delta minus delta to have it like between minus delta and delta. So to transform from 0, 1, the random uniform to minus delta plus delta, which is the allowed change I have in U. I create a mask using the probability. So I will choose 10% of the pixels. They have 1 and the other are 0. This mask will help me choose the 10%. And I will prepare the mutation and I will repeat it batch size. So I will have a mutation for each image, the same mutation. Here, the plus will serve to do the mutation, like delta or like a kind of between minus delta, delta chosen here randomly. So I have the mutated inputs. So I will predict I will predict on those mutated inputs using my model to collect the predictions. So I call here so synthetic predictions, and I will just, my failure rate will be how much the ratio of differences I have, and this average would be like yes, it's a kind of the sum of differences and divided by the sum of all the elements, and this is the mean what will return, and I will add this failure rate inside the table. So in the table, I will repeat many times on the same batch, and I will do many samples. So I have a kind of many samples, and for each sample, I will do this repetition. So how I will be confident if my model is robust enough? So I will do a 95 bootstrapped confidence interval. So I will took all these failure rates, which are averaged by the size of the batch here, and all those averages, I will do a bootstrapping here to return the confidence interval of 95 level, and I will take the high end here, how much I can go for it. So, and I will test if this high or less than the 20%. So it's a kind of have many different failure rates, and to have confidence enough. So I will do the bootstrapping with 95 level. So to see how much I think that at 95% of change, I will go to this kind of failure rate, and I want this to be less than 20%. This is a statistical test I do here to assert that my high end of the confidence interval will be less than the maximum tolerance, and I will run it. And this is my unit test for randomly checking how much my model is robust against white noise. And the exercise will be to adding, for example, test to invariance of rotation, of translation. And this is the idea. I will check this parameter generated randomly, apply the transformation, and do the same code. And after that, I will have another function here, which will say test robustness against rotations, or test invariance to rotations, because our CNN should be enough robust to rotations. So I have run one test and it's successful, and it's okay here. So we can push it further to have a failure. So maybe we can have a 5% here of delta, or 25% probability, and we keep the max tolerance. I think maybe the FNet will not hold on this parameter to see just the failure. And for this one, I call it average case robustness assessment, because we just do a random sampling of all the delta, and we choose a delta like enough low, I think, because it's a robustness. The model is not trained on this data. I think it's okay too, but yeah, we can do more. Here, 50%. And this, so this is the idea, is to have the average case scenario. But I will show in the search-based approach that we have a worst case scenario. And this worst case scenario is I will use a search-based algorithm to look for all the vectors of noise, and this is failed because I have 70%, I think, failure, and I expect 20%. Why? I just, to show you the failure, I just do 10% of delta, but 50% of the pixels. So I change 50% of the pixel, and this is even FNet, which optimized on this data, couldn't hold under this high amount of noises. But now let me show you the search-based approach. And this is kind of advanced way to test software even. So we do search-based approach, which are, for example, PSO genetic algorithm to generate for also those noises. So I will start by a random vector, but I will let an algorithm to look for all the vector that I can change, apply as a delta for my image and look for the degradation and the robustness. So I have everything ready for me here. The same thing. I don't have a repetition of random. I have here the swarm size because I will use particular swarm optimization algorithm, and I will have the swarm size, how much element I have in my swarm 5, and I'll have just 3 iteration, and I will take 2 samples as I did before, just to have a quick run here, and I will have a low maybe 0.1 as I have before, and I will augment it together 10% and maximum tolerance 20% to have the same configuration. I will use really small API here to use. That's why I choose PSO. I will use this API. Just this is the documentation of all the API. It's very simple. So you have like a banana here. It's like the fitness function. You have the constraints. You just have the upper bound and lower bound, and he will look for all the x1 and x2 to have the best value of this fitness function, and it's working for minimization. I will use just this API, which is very simple, to do my search-based approach. So here, what we have a fitness function. So I will look how to develop this fitness function. Otherwise, I have everything the same. What change here? I will prepare the mask. I will fix the pixels. I will prepare the lower bound, which is the minus delta multiply with this mask, and the upper bound, which is the delta positive. So I have this mask, like we have just the mask, we generate 1 in some pixels, which is just 10%. After fixing this one, I will multiply by minus delta, multiply it by delta, which will be in my upper bound and lower bound. I will give it to the PSO and say, okay, look for all the delta that will have the best fitness here. And I will fix it with swarm size and max iteration. And that's it. I will collect these failure rates I found. I pass the failure rates here as argument. So it's a list. This list will be filled by the algorithm because I do the failure in the fitness function. So I provide the fitness function, and the API will do this collect for me. And I need this failure rate to compute the bootstrap confidence interval. So here I have the model under test, the batch, and the failure rate from the arguments. I will pass it from my main code to this function, and this function will do just apply this delta. I have 1 delta. I duplicate it for my batch size. I apply it to the inputs. Then I will predict. I have my synthetic prediction, synthetic probabilities. I will explain why I need the probabilities here, because I need a fitness function that fine grain. I cannot do a fitness function that might be 1 or 0. It's working, it's not working. It's not smooth. I cannot optimize on it. So I need a smoothness here. I need a distance function. So I take the probabilities here, and I will Jensen-Shannon distance, which is a divergence distance between 2 distribution of probabilities. And I know I have a softmax that will output a normalized output that it's a kind of distribution here, like between 0 and 1 and sum of 1, all of them, and which have a kind of probability of being assigned to this class. And if I have this, I remove just the non-function, because when it's very close to 0, the probability, it can be turned to none, not a number. So it's a kind of numerical instability here. I remove it. After that, I compute the average, because I have a batch, so I have a 32 elements. I apply the same transformation. I compute the distance of all the vectors I have. So I will do the average here to have a fitness. And as I said, it's a minimization here that's provided by the API. So I will do minus my fitness. I want this fitness to be high. I want the distance to be more, and I have a high gap. So I will do minus fitness. So I don't look for the X best X. The X optimal here, what's the X optimal? It's the delta, the best delta that give me the best distance. I don't care about it. And the fitness, the value, I don't care about this value too, but I need to fail this failure rates. So that's why I have this line. I predict I will fail how much failure I have, each fitness. And if for each fitness, I have an evaluation. And before continue evolving over the population, I will collect this failure rates. So I don't care about. It's not really an optimization here an optimization problem, but more than exploration and guided exploration. Once I have this, I will run it, and it will be very heavy and like not worst. It's worst case. It's not heavy in the running, but it's heavy in the way that we'll just looking for this. This system. And I will run this one. Everything is the same. That's why I don't look in these details. So I will just kept 1%, 10%, tolerance of 20%. Good. Okay. We'll see if it's those are just the inference, because Keras, when we use it, here he found not a number, as I said, but it's I already do the function that will remove those not a number, so we will have a stable result. And it's okay. So let's do 5 here, 5, and probability maybe 25%, which is not working for the random. I hope it's working here and show you the power of doing search-based approach instead just a random. And yeah, this is the idea. And for the exercise, I put in the README the exercise. I give you all the transformation here, and I was expecting that you add, for example, test row invariance or test robustness against different transformation, and you just need to use these parameters. And once you have, like you decide if you want to do random, you just sample this variable around upper bound and lower bound with just NumPy random choices. It's failed here. You see, it's more powerful, and it give 23% of failure rates because he find more like noises that are significant, which is random fail on this configuration. And or if you want to do the search-based approach, you should like trick this function as I did here, and you change the sigma, and after with that you have all this against this transformation, and you will be enough confident that your CNN or how far or how to which extent is robust really by playing with this parameter and run all your full test. And if you have a pipeline of MLOps, this will be one of unit tests with robustness that will run automatically on your integration server. And our research, Deep Evolution, which is a library that will have 10 meta heuristics, not just the PSO provided, and all the transformation on audio files, images, and text. And we'll have even the combination here. I don't discuss because it's a unit test. So we did even the combination, and it's really it's a tool that can be used directly and will be published soon. We are really in the final steps of just finishing the paper and publishing the tool, and this is what Professor Putz introduces. And but just I give you here a hint are the best like the best starting point of understanding the powerful of this kind of automated tools by using the generation yourself if you want to do unit testing, and how much is laborious task to do it for all the transformation. After that, you can do like test robustness against rotation and the translation, or all the transformation. You want to check all the combination, and this is all provided by nowadays like automated testing. And I will let Johan explain how to do a coverage, which is like how to compute really more fine-grained the deviation, because here I show a black box testing that I look just the output and the divergence of the softmax, and now we are looking more how to compute the divergence even at the level of the neurons before even seeking for the differences in the outputs. Thank you.
Thank you. Need the HDMI.
Yeah.
Any question?
What you Yes.
How do you set those kind of conditions on the level for your production? And do you think given the case of the landmark model that we're acquiring, would it be possible to basically
Yes.
make sure that the train and test choices
Yes, so I use just the noise and we play with the parameters, but what we did in the research, we use the same in the data augmentation. We do the translation with the data augmentation. We have the same parameters when we train our model. So we expect this is a kind of the inside the requirement, because in your requirement, we have the training data and we see the developers, they put this data augmentation to improve their data set. So we have the same requirement. So you expect your model to be robust enough to this data, and I pick these parameters and I do the unit test. So we make sure that we are robust enough against those, even when we already train against those. And we see that the search-based approach will always find like one vector of noise or a certain angle with a center translation that the model couldn't generalize on it. And this is like a weakness because we have the same object and the CNN should be able to predict this class. But we do like the confidence interval. So we do just statistical tests because we know our model is statistical and we just verify if it's robust enough or not. So yes, this is the MLOps pipeline that we expect. But we have automated too, because I just saw the unit test, but imagine we have an automated tool that just will use many different algorithms, and you will do the combination of all the transformation. If you like we did in the data augmentation, we apply multiple augmentation there, and we look for all the parameters to check if we are robust enough or not. So this will have insights on how improve our augmentation or do more training on it or improve our robustness.
Yeah, maybe I can add some comments to this. Yeah, so yeah, regarding how to what's the transformation usually yeah, you can in specific domain there are two things. One is the general noise patterns that commonly exist, for example, in the image cases, like those kind of white noise location, these commonly happen. And on the speech recognition side, for example, have audio, then really on those kind of levels you have a lot of very general kind of noises. Like others, like in the IoT or network communications, you have those kind of noises. So these are kind of somehow in a specific domain in general, but it can be domain specific. So how to extract those kind of transformations need some kind of knowledge and domain expert to get those out. And then those kind of things can be helpful for the testers to see what's happened to my model, when this model is applied in that noisy environment. And yeah, indeed, in the training phase, we can do the augmentation of the data by adding those kind of noises. But it depends on how you train it and how you do the augmentation. It's actually very complicated problem. So yeah, so here we mostly focus on the testing part, and those kind of noises are used for us as a way to generate the test data to see how the model operates or performs in the operational environment. Yeah.
Okay, thank you. Thank you. Any other quick question before we move to part 2? Did you try it when he was working? Did you like for?
Yeah, here I think we have a website and yes.
Maybe I need to like share. I will show later.
Okay.
I will just like give a brief introduction here. So first, I want to thank for the organizers and all my collaborators to make this work practical. And before we start, maybe we need to first like introduce ourselves, because Zhijie and I seems to jump from nowhere. Our name is not on the schedule list, so we will just give a short introduction to ourselves. And here is the QR code. You can scan the QR code. We have a website. All the code and relevant materials are there. You can try them yourself. And so now I will give a short introduction to myself. So I'm currently a master student at the ECE department at the University of Alberta, supervised by Professor Lema. And I was originally at the Beijing University of Post Telecommunications for my undergraduate level study. And now I'm like
thinking about when and where to take my PhD career, because this is a really important choice in my life, and I leave my content here so we can discuss more about more. So I will give you an introduction to what I have done so far. So at my undergraduate study, my first research work was on blockchain. So I was doing some research on the security issue on the blockchain, doing some empirical study about the security issue on blockchain. And this work was published at Symmetrics 20, I believe. And after that, I was lucky enough to join the Microsoft Research HR as an intern to study the formal method for deep neural networks, the certification for DNN against adversarial attacks. And as soon as I began my study there, I soon find that the formal method, the scalability of the formal method is actually a big problem. We can't apply such rigorous guarantee for big models. It's now we are working at the industrial. So next, I turned to my master program, and I was doing some work on the quality assurance for the AI system, especially on the testing for different models. This is exactly the topic we are now talking. We are to focus on today, and I try to find some practical solutions for the quality assurance for AI system. But I soon found that the DNN testing is somehow more empirical. We are trying to, because we can't understand different deep neural networks from the fundamental mechanism. So we are doing something more empirically. This is a useful tool to understand to do the quality assurance for AI system, but I currently feel that it's finding correlations, not the reasoning behind this quality assurance method, this testing for DNN. So I'm currently stuck here. I don't know where is our next direction. So it's confused me a few months, and I jumped out of the box to find more possible work to do. So I spent the last 6 months on bioinformatics projects, studying about how to apply machine learning models for structural variation detection. And I also participate in some deep learning compiler testing projects. And also maybe in the few months I will participate in distributed system testing. So all this work I showed to you was to want to find possibility for collaboration, the discussion or any kind of collaboration like this, and feel free to contact me. So finally, before we start, I want to emphasize 2 points. First, this tutorial is designed for beginners. We assume you have no necessary background for this AI testing tutorial for this. Yeah, and the second is this tutorial is originally meant to for a much longer period, so we need to skip some of these parts in this tutorial. So let's begin. Yeah. So what I'm presenting here is the fit-for neural net testing, and I will mainly focus on the coverage part, neuron coverage part of the deep neural net testing. And if you're interested in the background or related literature, you can check the paper, the Deep Golf paper and the Deep Hunter. They are very relevant to our tutorial today. And if you go to our website, this notebook is run on my local machine, but if you go to our website to check the notebook, we can actually pack everything you need in a compressed file. So all you need to do, if you have the Colab environment, all you need to do is to follow the code block here, and it will automatically load the necessary popular function for you. It's pretty straightforward. So let's try to see. Yeah, so before we start, I want to introduce some like motivation for why we need to even talk about testing for deep learning. So as we have seen earlier, that the development of machine learning system actually have a very similar process with the software development process. So actually, you usually first train a model, and then you evaluate the model. You see if there is any bug or the model is incapable of a certain sort of data, and you do the debugging. You enter the debugging phase. You may collect more data. You may change the model architecture to make this model more powerful or suit you, or more powerful enough to suit your need. And maybe you need to do this retraining process. So what's the problem here? The problem here is like the evaluation sense, the data for you to do the evaluation is usually limited because as in the data centric area, so it could be very expensive to collect label data. So because of this, it's usually hard for you to cover all the corner cases when you actually deploy your system. So to solve this problem, we usually need to develop a method to generate more test cases. And so for the test generation process, like in traditional software testing, we need to make sure that you are generating valid test cases. You are doing something that is semantically valid. For example, if you are testing your digital recognition system, you can't just put a cat image to test this digital recognition system. This is something that you need to keep in mind. And so the next phrase is, let's suppose that you indeed have such a large enough test set. So the next question is, how can we tell whether this machine learning system has been comprehensively tested or not? Or in other words, will there be any criteria to tell us when the exact timing to stop testing, and how to tell whether the system is actually well tested? So we know for classical traditional software, we have a metric called code coverage. So if we know that like every logic branch in this program has been covered, we have more confidence to see that, yeah, this program has been comprehensively tested. So in short, there are two questions we need to cover. The first is we need to define a testing metric that is suitable for testing deep learning models. The next is to find some possible test case generation method to guide you to to generate more test cases. And you may find that I switched the order in the to-do list compared to the introduction part, because first of all, our focus is on the testing metric, and I personally think that to do something, to find some useful, to do something first, you need to first define the aim, first define the metric you want to maximize, and then to find some method to try to maximize that aim. So I switched the orders here, and so let's now dive deeper into this testing coverage metric for the deep learning models. So the data set we're using here is the MNIST data set. We have seen this data set yesterday at the wonderful tutorial also. So I will skip the introduction for this. You could see that the image in this data set. So we can load the data into the data loader, and here I want to briefly tell you the input sheet of this data set. So it's kept in the format of NCHW. So the N is the number of the data in one batch. C is the number of channel. So for the MNIST case, we are dealing with grayscale image. So the C equals to 1, and HW is just the size, the height and width of the image. So I emphasize the shape of the input because it's very important part to when you doing something related to the AI models. Okay, so about the testing metric. So we are dealing with about something about the neuron at the neuron level. We all know that the neuron represents a computing unit, a basic unit in the deep neural network. So I want to introduce a metric based on this basic computation units. So as I said earlier, you can check the paper deep gauge if you are more interested about really work. And so why should we care about the neural level coverage about the deep learning testing? So in implementing world, we know the behavior of the data-driven model is usually defined by the distribution of the training data. So to measure how good the test data set is, you should you can compare the model's behavior on the training data and on the test data sets. So, and as the neurons are the basic component in the end, so we can understand the behavior of the model by analyzing the status of the neuron. So this is the basic logic behind the neuron level coverage criteria in the deep gauge criteria. And the status of a neuron, you can find many possible solutions to characterize the status, the distribution of the neuron, the output of the neuron. So here I will want to introduce a very basic and easy to understand neural memory coverage metric for you to help you understand the whole workflow. For some of you may be familiar with literature, there is ongoing debates on whether this so-called neural level coverage is useful or not in the testing. So if you are interested in this, there is actually a work at FSE questioning the usefulness of this neuron coverage. So I personally love this kind of work because it reminds us of what we are doing now. But in this tutorial, we will stick to this neural boundary coverage metric because it's really simple. It can help you to understand the whole workflow of this testing process. So what is the neural boundary coverage? In this notebook, you can check them later, or if you're interested. I gave some formal definitions for this so-called neural boundary coverage, but I think I can just summarize it to you with some simple sentences. So for this neural boundary coverage, we first compute the upper bound and the lower bound of the output value of a neuron in a deep neural network on the training data. We first keep that some dictionary or some data structure to store such information for reference. And then we evaluate the model on the test data sets. We iterate through all the test data points and compare the each value against the boundary of the new output value of the neuron on the training data set. And if it is larger than the boundary, we can record it as an upper corner neuron. And vice versa, you can record it as a lower corner neuron. And we like to count the number of these neurons as the number of upper corner neuron and the lower corner neuron. And we divide with the all the numbers of the neurons in the deep neural networks. And we have to to time two at the denominator. So we can make this coverage criteria in the range of from 0 to 1. So it's a very basic idea, and I believe you can understand it quickly. So in the following, we will try to implement such neural boundary coverage. So to begin with, as I said earlier, we need to find the distribution of a neuron on the training data. So we need to do first profile a deep neural network. So in PyTorch, this notebook is based on PyTorch. So in PyTorch, there are usually two things that you can do. The first one is to rewrite the forward function. So for those of you who are not familiar with the PyTorch in the it usually inherited from the N module class, and it has a initial method. It usually contains the layers, the deep neural network in the initial method. Like in this network, we have some convolutional layer, we have some activation layer, we have some linear layer. And in the forward function, you just define the order of the computation in the forward function, and that is enough. You can this is a network you can train, you can test, you can evaluate, you can do everything you want. So our goal is to profile them, to extract the intermediate values of them. So we can just rewrite a similar function as forward function, and I name it as the feature list function. It takes the input of the DN as its input and outputs the original output of the forward function, and data structure out list, which contains the output of the intermediate layers, and a name list, which contains the name of the intermediate layers. So I have already provided a name list here. So all we need to do is to append the out list for every computation inside this network to append this list. So you may notice that here are some things strange in the window, because in PyTorch there are data structure, usually a container that contains a number of different computation inside the container. So actually because we are computing some boundary coverage here, if inside the container we pass it the value through a value activation, it may somehow turn your negative values into zero. It may influence how you lower polynomial be computed. So what we actually doing here is to separate the computation inside this container. Here we first do the convolution and record the result, and then just continue the other computation inside this container. And we can record all the results, and we can see some we initialize this model. We initialize this input with some random value, and we can try to see if do a sanity check to see if we are doing right thing for the feature list function. So here is a third close to see if the output is the same, and to see the shape whether the shape is matching. So everything works correctly, and this is one of the approach you can do. It's very straightforward. However, if you are dealing with something that such as a deep neural network containing hundreds of layers, it's very tricky to rewrite this forward function, and you may make a mistake in the process. So from my personal perspective, I will not do this forward rewriting style work. So I will use a mechanism called FOOP in the PyTorch. This is a very powerful mechanism that you can take advantage of to extract the intermediate values of the deep neural networks. So we can first take a look at the documentation here. So nearly every module in PyTorch has a function called register module for the hook. It's reject this hook function for your module. And when you do the computation, it will first call the forward hook and pass the input and output value to the hook function. So you can modify or you can record the hook the value for this module. And so basically, a simple thing for you to do is to keep a global variable, and when you compute the forward hook function, you store the input value to output value to the global variable, and you can just extract the values from global variables. very straightforward. However, I personally think that it's somehow not so elegant to put global variables everywhere. So from my personal perspective, I will write a class called book recorder to do something like this. And you can like check the notebook if you are interested in details. So basically we have like inner function to help you to do the dirty work to extract the values in the intermediate layers of our network. We have some like register function. We have some interface to you to extract the results. So like we can give it a try here. Yeah, so we can, it's a very like powerful tool for you to know what exactly happens inside this neural network through this hook. So okay, so this is just like we have known the basic knowledge to profile different neural networks. So let's to see how exactly to profile the on-chain data sets. So we have a pre-trained model here. We load the model to the notebook, and we have a function called profile given. So it has actually two inputs: the neural network, of course, and data loader. This data loader class, when you iterate through the data loader, it will return the data and the label, and you can use it to compute. So for this function, we can return a data structure called dictionary, which contains a mapping, a layer name and a neural ID as the key, and the range, the minimum value and the maximum value of the neuron. So we'll like simply go through this process. We first put the neural network into the evaluation mode. We initialize this dictionary as our final output, and we iterate through the data loader. It will give you the data and the label through the data loader, and we like call the feature list as we implement here, implemented earlier, for the to extract the intermediate values in the neural network, and we get the result, the normal output, the intermediate output, and the name of the intermediate output. So for every layer inside this output list, we will iterate through all the layers in the output list, because we need to compute the the boundary of each neuron here. So we first like extract the name of the current layer, because our return dictionary requires such mapping here. And the next thing we need to do is to actually compute the number of neurons for every layer. So we check the shape of the every outlet at every layer, and we ignore the first dimension, because as I said earlier, the first dimension is the batch size. It's like irrelevant with the number of neurons in the neural network. So you multiply with the rest dimensions, you compute the number of neurons. When you get the number of the neurons here, you can like give them ID, like to iterate through all the neurons here. And here, the next thing we need to do is to actually compute the range of a neuron for this in this neural network. So what we do here, the input is the batch size and the 3 dimensions, and we first like to change it into a 2-dimension vector, and we take the maximum and minimum value in the 0 dimension over the batch size dimension to find the range of the value of the output of the neuron for every data point. So we call the minimum and maximum neuron. So the next thing is very simple. So we just compare the maximum and minimum neuron with the value in the recorded dictionary. If it is it's larger than the old maximum value, so you replace it with the new larger value, and vice versa for the minimum value. So it's pretty straightforward. You get this lower bound, upper bound, and here is initialization for this data structure. So it's pretty simple. So through this function, we can actually get the results for the profile process on the training data set. So let's give it a try. So it will run slowly here because we are iterate through the entire training data set. Let's wait for a few seconds. Some of you may question about this technique because it requires training data, and sometimes you can't get the training data when you analyze some commercial model. And I would say such kind of problem may be an open question for this testing of DLM models, I think. So let's just wait a few seconds. Okay, done. So we have get this kind of data structure here, and maybe we can explore this a little bit. We can see the layer of the model and the ID of each neuron. So the next thing we need to do is to actually we have done everything on the training data set. So let's move to the test data set. For the test data set profiling, everything is similar except that we have a network, we have a data loader, except that we have a data structure that keeps every information we need on the training data sets. So we can go like a similar process in this profiling function, except that we will compare the lower bound and upper bound with the values in the dictionary, in the data structure we have got on the training data set before. And if it's lower than the lower bound or larger than the upper bound, we will record as a lower bound neuron or upper bound neuron, and we compute the number of these neurons. And then we follow the formula before, compute this function. If you can recall that we have definition here, we just compute this equation, and we get the data. We get the result on the training data set, test data set. So we may need to wait for a few seconds for this function to compile on the test it. Okay, done. So our coverage here is like 0.14 or 0.15 if you like. It's pretty low. So until now, we have like cover all the basic information, all the basic workflow for you to compute the coverage of neural network. So next thing is how to find like generation methods, generate more test cases to maximize this coverage criteria. But because of the time limit, we won't cover too much detail for this. I actually write some explanation for the generation method. It's all from the deep Hunter paper, I think. I write some like definition algorithm, and I have provided some necessary comments for you to understand what this process is. But it's somehow like beyond the scope of this tutorial. So we can just like for now we take this as a black box, as a box method that you can generate more test cases, and you can yeah. So this generation method is actually like doing some mutation on the input image, but want to keep the original semantic of the image. Like there's number 5, so after the mutation, the image is slightly different than the original, but it is still the number 5. So we can get rid of the oral problem. We can know the ground truth. We can know the expect behavior of the system instantaneously. So let's assume that we have done something which is described very detailed in the deep counterfeit. So here I try to like enlarge the test data set. We have test image which contains the test image set which contains the original test data in the image. And for every test image, we will do a mutation for once and record this like mutated image in the new test data. So we have like double the number of test image here, and we can again test this coverage here. We can see if we double the number of when we double the number of test images, what kind of coverage can we get? So we need to wait for a few seconds. Okay, done. So you see that our coverage reached 1.0. It's the maximum coverage we can get. So it's actually astonished because we only double the number of test instances, but we get the maximum coverage. It's a very surprising result. So, however, maybe you cannot find such good results on a more complex model, on a more complex data set. But I would say it's still worth trying for this. So I think this is the end of my tutorial, and thanks for your attention. And I'm open to any questions or any comments.
Thank you. Thank you very much. Questions? Did you try? Did you have a question?
My question is, usually we after training a model, we have fees for testing purpose, right?
Yeah.
For example, the metrics of tools. Why you develop a new method for this?
So let me think about this. So the problem is, yeah, you have evaluation metric for like accuracy for this model. However, let me think about this problem. So first of all, from another perspective, we need some guideline for this testing. We need something that beyond the accuracy to guide our test generation method. So accuracy is something that's not reflecting the actual behavior of the model. You do not know. Maybe this model is incapable of one sort of data. It's like how should I say that's like limited perspective. You can only understand this model through like accuracy, but through this neural coverage metric, you can understand more about this model, what is going on inside this. So if you are interested in related work, well, I believe there's something for out of distribution detection using the neuron activation, using the using this status of the neuron. Like there is some work about adversarial attack based on the neuron status. So accuracy metric and the activation, neural activity is a two perspective for this model evaluation and model robustness, I think.
So maybe I can complement it. So the idea is the accuracy you get is on the specific test data, right? But it doesn't reflect the distribution where you deploy it. So what you want to do when you test this model is to have a sense of how well the model will actually perform when you deploy it out of that specific tested data. And the idea of neuron coverage is that you want to play the decision logic of the model and observe how the pattern of neurons behave. And the idea is, if you observe enough the behavior of the model, and through this observation, the model provides sound signals, you are confident in the performance of the model when you deploy should be increasing, right? And then by playing with this neuron pattern, if you observe corner cases in which the model misbehaves, then you catch some logical, some error in the decision. And then you can even use that to generate data to actually better regularize your model to improve the robustness of the model. So that's the whole point. Just the process.
There is some progress for the development, right?
Yeah. That's a big question.
My question is, how much robustness you can gain by increasing the neuron coverage, and how do you verify it becomes more robust after you increase the neuron coverage?
Okay, so we are doing like testing for different models. So we are not at the stage to improve the robustness. We are at the stage to understand the behavior of this model with respect to some kind of data and with this kind of specific data to understand the behavior of the model. So when you understand the behavior of the model, you can, in the next step, you can try to improve the performance of the model. Like you can, as I said earlier, there are some mutation methods to generate more test cases. And if you like, you can try to retrain the model with the augmented data to try to improve the robustness. It's a naive method. And from another perspective, you design a model architecture that is more robust, then you can again try to run this testing and like some benchmark for this process to tell you as an indicator to tell you that your model is more robust. So it's at the evaluation process, not the retraining or the robust improvement process.
Result of the evaluation of the coverage.
But how could I know it is a good method to evaluate?
Yeah, this is actually a good question. So as I said earlier, there's an ongoing debate on whether this metric represent the true action, true status of the neural network. But I think that there are some related work like telling you this model is the coverage model of this model, using the coverage of the model as an indicator for the adversarial attack detection. So we can actually use this accuracy of your detection to tell whether this coverage metric tells you the enough information about the behavior of the model. Using like surrogate task to tell you this.
Okay. Yeah. Quick question. Actually, the first comment. I think it's a very interesting work focusing on the behavior of models, and not only help us see how different
yeah.
But also use that for drift and smoothness of the changes in behavior. One comment is before that question. I realized that you changed some codes in the model to focus on the activities of the logics. Capture values.
The extraction process means to not influence the computation process of the own.
I just one more comment because you could get that for speed. Not if you compare the model to, for example, TF5 and that flat
yeah.
Then you could directly get the sensor values upon both of the models without changing the code. So that helps you with the black box, evaluation of the AR model.
Yeah.
The only cost there is your hardware acceleration that you have abilities in order to leverage the hardware acceleration. So it's not natively available like you
Yeah. So that's a good comment. So so the reason why I talk about PyTorch here is I somehow observe a situation when our new like master students are switching from TensorFlow to PyTorch because PyTorch is much simpler. It's easy for you to implement a new model, to try it out, to run the computation, to run the training, run the evaluation. So I think it's necessary to bring this point to those who are not familiar with this process so they can quickly get familiar with the DNA test. Yeah.
Thank you. Thank you very much. One more.
Okay, thank you. A quick question. Okay, thank you. Is there any like a study of proof on the correlation between the neuron coverage and the generalizability of the model?
Okay, so yeah, just as I mentioned earlier, it's an ongoing debate, and if you check the paper at FSC, I think 20 about its conclusion, it's actually questioned this correlation. It questioned whether this coverage metric represents the actual behavior of the model. If you take the conclusion and take this the takeaway message in the research question, in the answer of the research question. So I encourage you to take a look at this paper, and I think it's interesting direction to explore.
I will add just the interesting conclusion from study like that is like the diversity from the lens of the neural network. This is the good thing, because we can change a pixel, but if this input is diverse or we add adversity, if it's different enough from what we have, why we did this pixel perturbation instead of the others, I think when we have a coverage, this proof of diversity from the lens of the model itself, from the status. We change just that, and we change all the coverage, or we cover new neurons. This is enhanced diversity. So we go for more diversity, and this is proven by looking at the activation. So it's a truth from the inside of the model, instead of just looking for in the high dimensional of the input, if this pixel meaningful or it's and add certain diversity in the behavior of the model.
Yeah, I also have a comment.
That's a very better topic in this model.
Yeah. So actually, this is a question I have been thinking about for many years. So since we've done a very.
I did the whole page.
So I'm not sure whether you are aware that in 2014, Reformist colleagues had a paper on the correlation between the fault coverage and the line coverage, branch coverage, and fault detection capability. If you are this paper, you can look at that. It shows a very surprising result in traditional software testing. The code coverage we have been using for many years is in that paper. The claim is not correlated with the fault detection capability, but that doesn't impact that how we continue using the code coverage as a very basic part for testing as a measurement of the testing sufficient and quality. And I think a similar case is also here. So I'm not arguing that this criteria is good or bad, but I think this is a really important first step to understand the behavior of the neuron and the neural network, and how can we make it useful in your case, and for example, as a guidance indicator or feedback or for other purposes. I think that really depends. And the correlation analysis, to be honest, I'm not very sure whether that could be also happen in this context. Suppose that the claim is true in kernel software, we don't have such a correlation. So, but I think no matter what cases, we just want to show that this could be useful for your understanding and useful for testing. I think that's maybe the first path we can take out of consideration.
It's improved your understanding of the behavior of the network. But recent studies by Miriam came out, I think, showed that the correlation with fault revealing capacity is very low, but it's still a very useful for exploration. Okay, so it's a topic that generates quite some discussion in this small AI testing. Okay, we'll move to the third module of our training, right? And then we'll have here.
Yeah. Can
It's
everybody
our
hear me?
tutor. I can.
Okay, yeah, so I think we are a little bit running late, but before I started, I just do a quick introduction about myself. So I'm a second year PhD student at the University of Alberta. And before that, I obtained my master's degree from the University of Waterloo. And before then, I did my bachelor in Beijing University of Post and Telecommunications. And here is the QR code for this notebook, and also the notebook you can use. And there is my personal website, but I would say not much information there. But just you can find my contact if you have any questions. Okay. Oops. Okay, so previously, both Hosam and Yuheng, they are talking about testing and more mainly on the feed-forward neural network. So here in the last part of our tutorial, we will focus on the stable deep neural network analysis and testing. So in this tutorial, we will explore how to quantitatively analyze a stable neural network. And to be more specific, we will work on an iron model. So our materials will be highly relevant to the paper Deep Stella. I think it's only SE 2019. If you're interested in more details, you can check out this paper. So here's a brief content of our today's next session's tutorial. So first, we will go through the implementation of state abstraction, which is a key component in Deep Stella. So there's some concepts here, and I will go through a little bit later. So, and then we will implement a function to obtain the trace given the abstracted, given the implemented abstracted model and the new text. And next, we will implement two metrics for measuring state-based trace similarity and transition-based trace similarity. And last, we'll use this data to analyze adversarial attack on text data. So here, I should first give a brief background about the model and the task. I think almost everybody should know something about the iron model. And so in this tutorial, we will considering a much simpler task. It's a multi-class text classification. So the data used is a news data set, and in the data set, each text is labeled as one of the following four classes: words, sports, business, science, and technique. And then let's just consider using a simple iron model. It's one layer GRU model, and the hidden state size is 256. So since like the training and iron model is not the focus of our today's tutorial, I will just skip this part, and we have already done the training for you, and the accuracy is like something around 91.5%. I think it's pretty good for an iron model. So here's the architecture of this iron model. So first take the embedding, and then go through the GRU module, and then take the final hidden state to a linear layer, and finally go through this softmax to get the prediction probabilities. Okay, so now let's try to load this model first. So I already have these files on my computers, but if you are using the Google Colab, you should comment out these two lines to load the list files. Yeah, so let's load the training model. Okay, so now let's use a very simple example to see how we can use this model. So here is a text, it's a news text, and then we have, because like the prediction will be like arbitrary numbers like 0, 1, 2, 3, and we just transform it into the text. So for an iron model, and given the input text, the first thing we will have to like tokenize this text into several tokens, and then we'll just go through the prediction. So here, I would say that the fantastic thing here for the iron compared with the CN or for the PyTorch is that they already help you give you the all the hidden states inside the model instead of only the last hidden state. So you don't have to spend time like using hook function to get all the intermediate hidden states. And then let's try to predict on this text. So you can see that for this sentence, the prediction label will be science and technology, which I think is like this news about Yahoo introducing their new search engine. So now let's just do a quick recap about how Deep Stella analyzes an iron model. So for the deep data, the most important part in it is the state abstraction. So different from the feedable neural network. So for the ANA model, we're trying to execute the neural network multiple times using a single input. And our input is a sequential data, for example, like a text data or audio data. And then during the inference, we can get all of the intermediate hidden state. But like this hidden state are usually very large vectors. For example, in our case, it's a vector with a size of 256. And you cannot find two identical hidden state vectors in your training data. So what we do here is, first, we will do a dimension reduction to reduce the dimension of our hidden state vector. And then we do the interval abstraction, which is basically we try to group the similar hidden state into an abstract state. And then we can transform we can transform all of these hidden state into a limited number of abstracted states. And use this abstraction model, we can do some analysis, like we can calculate the similarity between two traces, and we can also like do coverage calculation. Yeah, I'll just go to this part. So here's some of these APIs I used in this notebook. I think due to the time limit, I will just skip this. But if you have an interest, you can take a look into this, or even like try to use this by yourself. So yeah, so now let's speak on the state abstraction in the deep data. So in the deep data, as we say, the first thing is to do. Okay, so the first thing we will do is profiling. It's similar to what we do in the feedable neural network. We try to use all the training data and then extract the intermediate prediction representations of the neural networks. So we call it step profiling. So here we first profile all of our training data on the model, and then we extract all of the intermediate hidden states. And then we use the PCA to do the dimensional reduction. And then next we will group the similar hidden states here. So you can see like we have like, for example, with here we use a relatively simple one. Just use just spell the vector into like m equal size grids, and then we group the similar and then we group all of the hidden states in one grid as an abstract state. And then after we have this abstraction model, we can extract the state transition between for one training data point about the hidden state transition between it. So okay, so now the first step is to do the PCA dimension reduction, but it's like, I'm not sure if you have tried it. It should be like take a lot of time. So here we just skip this part, and we already do the PCA reduction for you. And I will just load this data. Yeah, I'll stop here for like 1 minute. Anybody has questions or?
Like the PCA, like how to choose like how to choose K here?
That's a good question. So like here, how to choose K is really in the deep data paper, they do a lot of experiments to choose, like, for example, when you have a larger K, of course you will keep more information, but then if you go to the next state to scale it into n grids, your space will become larger because you have like more dimension. And here, so as a tutorial, use a simple one, we just reduce it into the 3 dimensions. But like I think they have the detailed experiments on how to choose the K and M, and it really depends on the task. and depends on the model. For example, like I think like for those like speech recognition model will be much complex, and in our context, it's a text classification and will be much simpler.
Yeah, it's more of a trade-off between accuracy and accuracy and also the simplicity of the model. So what we can easily do is that you can check when you reduce each dimension and how much information is lost in this reduction, and then you can get a better choice on whether you want to lose more information in this PCA reduction.
I was just wondering, I mean, you see you're using this for dimensionality reduction, right? So could you choose an another cluster you can use for PCA, like K-means or something else, or PCA was chosen for any particular reason?
Oh yeah, so mostly for simplicity and beginning, but actually you can choose any kind of the idea is that you move from a similar state to one and how to do that. You can do it manually at clustering and other
Yeah, actually for the second step about split this into n grades. Great. Oh, I think. There we go. Okay, so for this M split, actually we have tried to use the clustering method, and somehow it has better performance. But like for clustering, another problem is how to choose the class, how many classes we need. And so, but in this tutorial, we'll just use a simple one, use the M grid. Okay, I will go to the next one. And then, so as you can see here, so now we already have the PCA. Next step is just to spell this grid. And so the idea here is similar to what we do in calculated neural boundary coverage. Let's go to the code. So here, for all of the PCA data, as we say, now we have 3 dimensions after we reduce the dimension of the hidden state vectors. And then we just need to calculate the minimum value and the maximum value on each dimension. And then we can spell it into M different size of M equal size grids. And the next, we just project all of these reduced dimension vectors into these corresponding grids. So we can try to use this. And after we have already obtained like the size of each size of grids on each dimension, we can project all of our PCA data into corresponding grids. And now, so let's try to run our deep data model. And here we just set the size of the grids, the number of grids M as K. And so now we have our deep data model, and we have profiling our training data. So we might want to take a look about what's the state that our training data usually visited. So here we just run a simple code to like try to find which state the training data usually the most frequently visited. So we can see the state is the state 545, and through we find that usually the model will go through this state after in their first state. So it's kind of like the initial state, I would say. Like now, as we have our deep data model, and next we would like to like obtain the trace of a new given text. So let's implement this function to do this. So here, for new text, firstly we will have to inference on our model and try to profile all of the intermediate hidden state to our model. And then remember we need to first do the PCA reduction. So we will do a reduction on this hidden space. Then we just project it onto the corresponding grids, and then transform all of our hidden states into the abstracted states. So now let's try a very simple example. Everyone will try use the hello world to see like what is the trace and what is the prediction of this. I think like prediction without maybe doesn't make any sense. So we can see, let's see, like the trace is the first one is the state we just see most frequently visited is 545, and then after reading the second word, the trace just go to another state 555. So after we have this abstract model and we have this trace, we have this abstracted space trace, and what we can do here is we can calculate the trace similarity between two different input texts. So here we should introduce two different kinds of trace similarity. So the first one is state-based trace similarity. The basic idea here is take two traces and calculate how many states they're sharing and how many states they both visited, and also like the union of states of two traces. And another one is the transition-based similarity. This one is slightly different. So here we are not simply we are not only considering the state, we are considering the transition between two states. But the basic idea is the same. Find out like what are the transition those two traces are sharing, and also the total example of our traces. So after we finish all of this, we have some basic tools to analyze our RNN model. We have the abstraction model, and we have two different metrics of trace similarity. So next step, we're going to use this data model to analyze the adversarial attack. So here, let's take a look on these two sentences. So I'm not sure if you find like the difference between the two sentences. They're just one word different.
Defeats and
yeah, the first one is defeats, and the second one is just transform the defeats into the kills. And I think this is a very basic example of the adversarial attack on text data. And let's see like what is the difference between these two sentences in the RNN model. So we can find that they have completely different prediction level. So the first one, the original one, is predicted as the business, but the second one is predicted as a world news. So what we can do here with the deep data model, so we can try to take a look on its trace. So here just that's not a focus of our tutorial. It's more about something about plot in the Python. Yeah, let's take a look on this. So for the first one, let me see how can I group this into one. Yeah, I'll just zoom out a little bit. You can see like for these two traces, they're different, especially when reading the word. When originally it's defeats, and when transformed kills, like you can see like the model goes through a different state, and finally they result in different prediction. So now if we try to use the trace similarity to calculate the similarity of these two traces, we can find that for the state-based trace similarity is around 0.3, and for the transition-based trace similarity, it's even lower, it's just 0.15. So this is just a very simple example about how we can use the abstract model to analyze an RNN model. And based on this, we can also do something like coverage guided testing. But I think due to time we didn't prepare about this part. But if you are interested, the idea is very similar to what we do in the deep hunter. So aka the straightforward neural network testing. So, okay, so I think this is most of my tutorial, and I also have something. Just give me a second. So based on this data, we took a step further to make it more interactive. We hope to make the debugging understanding of an iron model to make it more easier for like non-experts. So we make the whole the whole process of this data into an interactive interface. Here's just some screenshot of this interface, and so hopefully next time for tutorial we can use this one to make it more interactive. Okay, so I think that's all my part of this tutorial. So if anyone has any questions, thank you very much.
Question, comment? You got a question? Any question?
Yes. Quick question, have you compared this similarity, like the result with those other basetimes, like for example, just comparing the last layer of these different models to check the similarity? Are they correct, or are they like what's the difference between? And I mean that's a baseline, I think, right?
So what we so let me try to understand the question. So you mean like the for example, like the features in the last layer of model, the difference between
like the last layer you have, like for example, like 64 units, right?
Okay.
You have like 64 values, but if two different, the including of two different 64 values, so you can have a similarity between those two. Right? Some people use those things to data type. So what's the this is another way that you look at the trace of different to give input to say the similarity. So is there a comparison between those two?
Oh, I think like in this context, like so for this iron model, we use the last hidden state and then go through the linear layer to do the prediction. So here, I think the similarity of this, like the result of last layer, might be slightly similar to like the last if they are going into the similar state at the end. So but from the result we find like I think that let's go through it. I'll try to pull out its trace. So actually they go to a very similar state in the last step of the model. So but I'm not sure if like trying to calculate such similarity is similar to the trace similarity or state-based similarity. Maybe like it's still, I'm not sure because I didn't do it.
Okay, thank you.
You may be more precise.
Yeah, more internals.
More questions? Comment? I know we're having a long day. Yeah. Okay,
So we compare neural coverage with neural. So the reason that neural coverage does not improve with false previous accuracy, but it's good because at least we need to recover the statement, and then after that we can hope for finding, good testing. And this might be the same for neural coverage. The one question I have is, have you also seen like the situation where you have on dead neurons, like not reachable neurons, and maybe some neurons cannot be covered and cannot activate because for whatever reason. In this case, what can we do after trying and see we cannot cover some neurons?
What is one? There have been some. There are some attempts to repair actually for those cases.
Yeah. So yeah, thank you for this is a really important question. So So after training, we found that some of the neurons will be always in the hyperactivity state. So always very, very nervous. Some of the neurons are in a very, very low activation state. So there will be always that. And there are some, not our papers, but other papers found that these kind of neurons, in particular those less active neurons, are somehow not that kind of informative. So they can be pulled away in some sense in the next evolution of like a model improvement or something. Yeah. So this can be actually helpful for us, like a dead code, maybe a dead neuron in some sense. That can be something. But how to deal with it, how to from architectural level or from the training perspective, how to improve it, it can be further research. So I want to stress that there are a lot of opportunities in the argument recently regarding all these kind of research on this. So I definitely encourage all of you, to go into it and figure out and find this important findings.
Jump in and contribute. Yeah, and maybe just one more bit on this general thing. Like there have been some studies also showing that pruning doesn't improve generalization.
Yes.
Yeah, they just prune them out. Like they decide on equation and then they prune them out. And then when you do signing and for generalization, you get like more robust model.
Yeah, when you remove this some of that neuron, it doesn't impact much on the accuracy kind of playing on your buttons.
I can add something because from the perspective of training, because we train on the data using the loss, is very lazy. So the training won't touch a neuron that doesn't affect this loss. So maybe there is a value that is the initialization. Maybe just we touch this neuron. But when we have an input that triggers this neuron, we have a misleading input. So that's why when we prune them, it's better for the robustness and we keep the accuracy. But maybe it's better to retrain it for new data. But if we stop at this data, it's better to prune this neuron. We have better accuracy. But when we use the test, we want to trigger this neuron because we know that we didn't use it for the training data and it's kept at its initial value or some adjusted value, and it can just like mislead all the outputs.
It's like dead code, right?
Yes.
Almost dead code, right? If it gets activated and you actually don't know what happened when it is activated, it could actually mislead. So that's why we want like to make sure we explore to see what kind of signal we get when we touch that. More questions, more comments? I hope you found the tutorial impressive. Hopefully, it's a call out. I think especially to the student, you have seen there's been many open questions. We're mostly approximating this test at this point. So more research is very needed on this topic. I strongly encourage you to join this. And I would say big thank to our tutors. For you. Okay. So I think we catch up on time.
Yeah, so maybe one last note is all the code links and every resource we covered today will be put on the website of SEMLA. So if you want to check out them hands-on by yourself later, you can do that after you come back home. Okay, thank you.
Thank you. Thank you, Lee. Thank you, everyone. And we have a short topic break. We'll keep one session. I know we're getting late, but that session is pretty fast. Of course, all the sessions. See you after the coffee.
That's fine. What's I think what's it plan? You'll come back.
哎，雷哥，来，雷哥，我现在给他发过去，然后这个就是关于这个 state 这11个人号对吧？我先寄给他，但是然后我 CC 你啊，没有我 CC 你，然后那个到时候就我收到那行，那你那个今天晚上那个你们我们是有一个那个玻璃窗的这个关于为这个。老没有，看你们俩。今天啥？实在比较都是。对。这是快断，都有这样。就是在那个上学的时候，好点。对，这个是从瓜亚里8点8。对，因为那个他那个是3，要么就是6点，他这个他就这样，因为早点他是。大家说一个这个。要我换一个，还是会晚上是一个，不确定。如果老板那个老板在这，老板在这个基本上。你2个他们做的， 行，每个类的我那个我发过去的，到时候确 OK，一晚上到时候去吗？我去吧。行，到时候我关你。OK。哎，你们说是这样，也不是啊。要不比我的电脑对我脑用那个电脑，对，我有 USB，也是 USB，我有这发给我。哦，行了，发我到时候差异的一个结果。还有。
Homepage. Go down. But I need to share my screen. Yeah, we present this. And also that and okay. Only share my like you want to that project like other like share my then connect share that's oh okay. We can show also I as a film circle, but I cannot share it. Hey, just 1 second. Okay, stand there. Stay.
Yes.
Should I start the video?
Yes.
Yes.
I think so.
It's,
One more minute.
the last line. But we have the video. We get more audience. Watching this make. Some of the talents.
Yeah.
They told me that they were-
So welcome back everyone. This is our last session of the week. So let's get started. We have Riley, who is a senior researcher at the Center for Software Excellence in Huawei, Canada, where he leads the team on software engineering for AI systems. He and his team developed the engineering technologies and guidelines to ensure the compliance, quality, and productivity in the life cycle of the AI system. He received a PhD in computer science from Queen's University and has published in prestigious conferences and being in the program committees of prestigious venues in software engineering. Without further ado, I'll pass it to you.
Can you hear me? Is this working? Awesome. Thanks for the introduction. I'm Dari, and I'm a senior researcher at Center for Software Excellence, Huawei, Canada. And today I'm going to give a talk about our exciting research on trustworthy AI engineering. So before we start the actual research part, I'm just going to quickly introduce our department. So we are Center for Software Excellence under the Huawei Canada Research Institute. We're located at Kingston, Ontario, and we do a lot of fundamental and frontier research in software engineering domain. And we currently have openings for full-time and internal. If you're interested, feel free to check out our website at www.huawei.com/ca/careers. So why trustworthy AI engineering? So AI engineering, although right now getting attention in software engineering community and also AI research, so already really hit it in academia, but there are still a lot of challenges that industry face when trying to develop an AI subsystem or solution. A lot of AI research focus on high-performing machine learning models, but in industry, a lot of challenges comes from different aspects. For example, how should we do asset management properly for AI systems? How do we do risk control and assessment? How do we make sure the system is compliant to all regulations? As well as how do we deploy the system and monitor the system performance? There is a Gartner report last year that actually highlights that it takes around 8 months to get an AI-based model integrated within a business workflow and to deliver the value. And the prime focus for organizations is actually to accelerate the speed at which the proofs of concepts move into production. In their hype cycle for AI 2021, several related demands were mentioned as well. For example, there's model ops and also AI orchestration and automation platform, which are all related to the engineering of the AI system. So this is our view on what would a trustworthy AI engineering perspective be. On the top level, there are several regulations, standards, and certifications coming out recently, and a lot of them are also under development and would come out soon, including the very famous EU AI Act, and also several regulatory bodies and standardization bodies like ETSI, ISO, and IEEE. They are all in this demand. And then to actually meet this regulation and the standard requirements, there are several business challenges, mostly broken down into 3 aspects. The first one is compliance, for example, the auditability of the system, the transparency of the system, etc. And then also the quality aspect of the product and the development process, including the functional suitability of the system, maintainability, reliability, portability, etc. And then finally, how do we develop an AI system in a productive way is also really really interesting to study. That covers the whole life cycle of developing an AI system, from design, develop, to build, and then maintain. So in order to solve or at least approach these business challenges, we will need to look into several engineering problems that covers a variety of unique aspects in AI life cycles, like data, feature, model, experiment, interpretation, and dependencies. A lot of them are not usual asset types that occur in traditional software. And then to solve them, there are a lot of different engineering problems covering the whole life cycle of AI development as shown in the slides. Not going to mention all of them, but in today's talk, I will highlight 3 parts that we are looking into as some examples of how should we approach trustworthy engineering. I'll firstly talk about on the data front, how do we do data license conformance, and also for model side, how can we reproduce a model training process, and finally, how can we derive a consistent model interpretation. So I'm just going to quickly acknowledge that the work I'm presenting today are not going to be possible without a lot of industrial colleagues and also academic collaborators. So the first part is on the conformance of data, conformant data usage. For more details about this topic, we also have a talk at this year's EU Open Source Summit that you can check out. We'll go into a lot more details than what we can cover today. But essentially, the problem for AI is that it relies so much on data, but the public available data are not usually can be directly used to develop AI solutions. There are several challenges when we are trying to do data license compatibility analysis for AI development. And the first one is provenance related challenges. So it mostly deals with where data comes from. For example, imagine a data set that's being created by crawling on several different sources, like different search engines or websites. They might be caught at different time points. Those sites might also collect data from different sites at different points. So at which point should we collect the license information from those sources is unclear. And then a lot of times when people are sharing data sets, they will be redistributed many times. And then the license itself will locate in various locations. Sometimes it's within the zip file of the data. Sometimes it's on the hosting website, etc. So the license location is also unclear. Finally, as I said, if they are distributed through multiple channels, there will be multiple copies and variants of the set hosted in different places that could label them with different licenses. That will also pose a challenge. And the second general challenge will be related to the lineage of the data. For example, when people are looking into using a data set, that data set might be created from sources that are unknown to us, and hence pose a issue of identifying what is the proper license to use for data. And then finally, how to identify the minimum licensable data unit is also very challenging. Like, for example, if the data set is composed of multiple different data sources that contributes multiple different data items, do we need to trace back to each individual item, for example, one single image created to trace the license lineage, or do we stop at the source level? That's also unclear. Finally, the license-related challenges relates to in data. The license actually is not as mature as open source software licenses, where the rights and obligations are clearly laid out. For data, a lot of times it's very unclear certain actions is permitted or not under an open source license. For example, if the data is not permitted for redistribution, would a model trained on that data be allowed to be redistributed? That's also some unclear questions. And then if there are multiple sources and there are multiple licenses, how do we interact? And what are the impacts of those interactions are also unclear. To solve these challenges, we have recently sandboxed a project under AI and data called Open Ecology. It mostly deal with all these challenges that we face when releasing or using data sets for AI development. For example, some efforts within this project include enhancing a data license schema that covers more rights and obligations for using AI data sets. And then also data license recommender and generator in case we release a data set. Finally, some portals for sharing the analysis results of data sets and licenses. There is a GitHub repository that's open for collaboration and contribution as well. I'm just going to quickly wrap up the data here, and for more details, you can check out the EU open source summit talk that we have. And I will spend more time on reproducible model training and consistent model interpretation side. And these two works has also been published on the latest software engineering venues. The first one, reproducible model training, is published in this year's Exceed. So you can also check out the full paper for more details. So we all know that AI is facing a lot of reproducibility crisis ever since a paper published in 2018, highlighting that a lot of studies in AI domain can actually not be reproduced. A lot of times they wouldn't release related code or data sets or experiment configurations, leading to the results not being reproducible. To understand this problem, we need to first define what would be reproducible. So essentially, if we divide a metric like the left bottom left corner, we would have data on one axis and code and noise on the other. If we can get this with the same code and same data, get the same results, or a model that has the same behavior, then we think this is a reproducible model. If we with a different code but the same data can implement a model that has a similar performance of behavior, then we call it robust, or there are some other similar concepts like reportable, generalizable, but we'll focus on the same data and same code part, which will be defined as the reproducible models. So even though that, even with all the artifacts being published, like even with all the data and the code, sometimes the results still cannot be reproduced. The models still behave differently from different training rounds, mostly because there are a lot of randomness in this training process. There are some other papers highlighting that even given the same model, data environment and code, the performance of the model or the behavior of the model still vary. So that would pose a challenge on a lot of fronts, like how do we debug the problem if given everything fixed, the behavior is still different. How do we audit the model training process if it's not even stable, etc. So just to solve this, we will need to understand that there are multiple sources of randomness and problems in training a reproducible deep learning model. The first part comes from the software. We know that both the framework, the environment, the packages that we use to train the model will introduce a lot of randomness. So that's from the software side. And then when we're training a deep learning model, a lot of times we will use GPU, and then GPU also would have non-determinism behaviors when they are parallelizing computation, which will introduce the unreproducible behavior of the model. Finally, there lacks a systematic guideline right now to instruct how do we produce a reproducible training process. There are some solutions right now, like we could try to specify some seeds in a lot of different levels in the code, which is very ad hoc and very hard to manage. And sometimes you can't even control all the software dependency from that. There are some environment variables you can specify to control the hardware non-determinism, but again, it's very ad hoc and sometimes doesn't really solve all the problems. And also currently there's no automated process to evaluate whether a model is reproducible or not. So we have a proposed approach where we try to mitigate the non-reproducibility of model training process by verifying the model reproducibility first in 2 rounds of training, and then checking whether it's reproducible or not. And if not, we will do profiling and diagnosing of where the randomness comes from and try to solve them on both the software and hardware front, which I will dive in later. And then if it's later solved through another round of training, then we're good. Otherwise, the process will be repeated until we reach the reproducibility of the model. On the software front, the way that we propose to solve the randomness without posing pressure on the developer to manually specify all the seeds is that we could use our method uses an API hook that essentially intercepts the system call to the randomness inside the operation system. And every time when the training process tries to involve a random seed inquiry into the system, it will be intercepted and it will be recorded whatever the system returns. And then it will be stored until when we need to reproduce the training process, at which time, again, all the calls will be intercepted, but this time we wouldn't let it go through this operation system. Rather, we will give back what was recorded last time. And in this way, we don't really need to require developers to specify the seeds themselves, but also records all the randomness within the training process from the software front. On the hardware side, there are a lot of efforts by companies such as NVIDIA to patch a lot of function calls at the framework level that could introduce non-determinism training process inside GPU. So we would do essentially a profiling of all the function calls within the framework, and then find out whether those calls are within the known functions that would introduce non-determinism in GPU level. And then we will apply those patches released by NVIDIA and other companies to try to mitigate this issue. So combining, here's a case study that we did involving several different types of CV models and one commercial model from Huawei on a different experimental setup. But essentially, we will show that with the record and replay mechanism we just introduced for the software side and also the GPU patches, we can achieve a 100% reproducibility for the models that we conducted experiments on. So that means that from 2 different training rounds, we can get the exact same behavior of the model that has the same inference results for all the testing data points. So the last part of the speech will focus on the consistency of interpretation, which is somewhat related to the reproducibility of the model behavior, but not at the prediction front, rather in the interpretation front. So to understand why interpretation consistency is important, we will introduce an example here. So imagine that you're a DevOps engineer and you need to schedule a daily batch processing job to run overnight in the cloud. But the weird thing is that this job sometimes will randomly fail. Sometimes it works out perfectly, sometimes it will just fail in the middle of the night and causing some downstream latency. So you ask your data team or analytics team to help in this case. The goal is that they can build a model to predict whether this job is going to fail in the next 30 minutes or not. And this model can be used in 2 ways. One is for prediction. So if the model predicts that this job is going to fail within 30 minutes, then you as a DevOps engineer can take action of resubmitting the jobs to avoid, to save some execution time and avoid further delays. Or you can also use for interpretation. So for example, maybe the model tells you that failure of the job is associated with the launch of a competing job from a different department. So maybe there are some issues within the scheduling that could be easily integrated if you just schedule the job differently. So you might reach out to the other team and schedule their job at a different time of the day, and the problem is solved really easily. To make this actually work, we need these interpretations to be consistent in 3 different aspects. The first one is internally consistent. That means that, for example, if the data team or the analytics team delivers this model to you, and now you have to productionize the model, that means you probably would feed it more data, and you have to train it again. But the problem is that this time you find out that the productionized version of this model compared to that one that they delivered to you gives you different interpretations. And the one you trained actually tells you that the competing job is not an important factor. So that means that like the interpretation is not consistent and you don't know what to do. And the different aspects of the consistency is external consistency. That means that the original model that they give you might be too heavy, and you want to have a lightweight alternative. This also happens a lot when people try to, for example, develop a surrogacy model to explain a non-explainable black box model. So can 2 different approaches solving the same problem in the same data give you a similar interpretation if they have a similar performance? That's how we define external consistency. Imagine that they give you a lightweight model that performs okay, but it's cheaper to retrain. But they give you a different interpretation. You still don't know how to act. So that's also going to pose a problem. Finally, the last aspect of interpretation consistency that we propose is about time consistency. Time consistency is introduced because a lot of times these models are not static. They have to be updated throughout the timeline to keep up with the latest patterns within the data. So for example, in this example, we will do a daily update of the model. What if the interpretation switch all the time, and like the model keeps overfitting to the latest part of the data and just ignore whatever trend that is in the historical data? So in that case, you will keep getting different interpretations and you still don't know how to act. So we did a study on these 3 aspects of interpretation consistency, and I'll skip most of the details of the study setup, but we came up with several take-homes that people can use when they're trying to do interpretation on a model to try to guide their actions. The first one is that we noticed that if we control all the randomness, well, at least from the software side, ignoring what we just proposed on the GPU side, and because that's something the last part. Here, if we control for all the software introduced randomness from the learner, from hyperparameter tuning or data sampling, we'll get a very steady interpretation of the model. And if we are not controlling any of them, there will be randomness or fluctuations on the ranking of most important factors. We actually noticed that the data sample introduces the biggest variation in interpretation. But the first lesson is that when we are trying to derive interpretations, we should control for non-determinism from the learners, hyperparameter tuning, and also data sampling by either manually specifying Cs or using the approach we mentioned before. Another thing that we noticed is that if we group a bunch of different models that's trained to solve the same task, that's the external consistency we were trying to solve, by their performance. So essentially we cluster all those different models by their performance. We'll notice that the higher performing models tend to be able to provide you with a more stable or more similar, consistent interpretations. That's both observed in the left figure, which is grouped by the ranks of the cluster. Also on the right figure, where we just directly plot the AUC of the model cluster against a metric that we use to evaluate the consistency of interpretation. And we see that when the model has an AUC of at least 0.75 above or above, at least in the domain of AIOps, we see a higher consistency among the interpretations. So that means that when we are deriving interpretations, we at least look into the model's performance and make sure that it's not lower than a certain threshold. That threshold might vary depends on demand, but at least the principle is that higher performing models are more trustworthy in this aspect. So that I will wrap up my talk here. And to summarize, I mentioned about our view of trustworthy engineering, mentioned about the 3 different problems varying from data, model reproducibility, and also interpretation consistency. And I'll be happy to take any questions. Thank you.
Thank you for the presentation. I have a simple question. So how do you think like the norm determinism in the, for example, like the randomness within the machine learning experiment result? Because a lot of time I have a feeling that the randomness is kind of unrelated, because people prefer to give the result just irrespective of the randomness. For example, like if your model really perform robust, then whatever the random seed is, it shouldn't affect much of the final result. Okay?
Sorry.
So I just want to know your opinion.
Yeah, thanks for the question. So I think if I understand you correctly, you're saying that the random seeds, when they are specified differently, it shouldn't impact the performance much, given a fixed code, right? So this is from a previous study, but on the left side of the figure, you see that a lot of times the random seed would impact the performance a lot, and random seed sometimes is even considered as a hyperparameter for tuning for this purpose, because like some study would propose a new model, for example, and then they achieve a really good performance in one run, and then they just report that result. But if we that would be the case for this figure, where we like, for example, handpick certain runs, and then it all performs better than the baseline. But if we do it more times and use different indices, we will see that actually that's just that's just luck. And if we look at the overall performance, it might not overperform the baseline by a lot. So so randomness does introduce a variation in model performance. And then another thing following that would be like, in that case, if we are limiting the random seeds in the training process, that limits the possibility of exploring just a better output of the model. And that's why when we're trying to solve the reproducibility problem, we're trying to solve it in a non-intrusive way, where we don't want the random seed to be fixed by the developer. Rather, the goal is that you can do all the exploration you want during experiments, and you don't need to specify that, or you can run it several times and you find the best performing round that has the best performing output of the model. But the goal is that now that we have a best performing model, we need to be able to reproduce this exact training process. If it's not reproducible, then it's not auditable. It's also hard to debug if there's any issue inside, because we can't reproduce the process. So that's what we focus more on. I hope that answers the question.
Thank you for that talk. So I'm very interested in data image. The community you are trying to work on. So yeah, I'm just curious. One example of how can you know where do they come from? So first thing is there are some regulations that restrict restriction on what companies come to with the data, and for example, what kind of risk is when it comes to when you want to use data. And also very interesting, what's the long-term plan that
Thanks for the question. So the first part is about what are the risks of using this kind of data in a commercial way. So I'm not quite familiar with all the regulation requirements on this front, but a lot of times you are restricted by the license, and that's what the project is focusing on. So essentially, like on the license front rather than the regulation front, how can we conform to all the license requirements or license rising obligations from data that you're using, especially given like all the more maturing practices and guidelines in the open source software community might not be directly usable within the data realm because of all the challenges in data license. And then for the goal for the long-term plan of this project, we just started this open source community. But the thing is that in order to solve all these problems, we not only need those processes, guidelines, requirements, we also need automatic tool support for a lot of those analysis into the license, into the data lineage, etc. So that's an area that we believe is very valuable and also needs community's contribution to move forward together.
Thank you.
Last question. Okay, let's have a round of applause. So the center is Annie Campbell. He's a research associate in Polytechnic Montreal. He's studying how software engineering practices can be leveraged to machine learning software system and how machine learning techniques can be applied for safety critical systems in terms of reliability and robustness. He received his PhD in AI from Iran University of Science and Technology, and before Polytechnic, he worked at UBS as a visitor, and he also was an assistant professor at the Alternative University in Iran.
Can you hear me? So let's get started. Thank you for introduction. Thanks for invitation. My name is Ami. I'm going to present. higher. I think that's it. I should take. It's fine now. Again, my name is Ali. I'm going to give you a talk about testing deep reinforcement learning application. I will present different approaches for testing deep reinforcement learning, from static analysis to mutation testing. And as already mentioned, I am working as a research associate in Montreal. First, let me reach my slides. Yeah. Let me acknowledge my colleagues at SWOT Lab. SWOT Lab is directed by Foods. So the work that I will present today has been done with a collaboration with my colleagues. One paper has been published with Mehdi and Hussein. Hussein is here, but he just got his PhD. And also we have a submitted material with Ahura and Florian. Also, we have ongoing project with Ahmed and Rashid about testing reinforcement learning application. So since yesterday, many of you see this slide about applying machine learning in different industries. Still, it is an ongoing project. Still, we have every day we see a new industry trying to adapt machine learning, trying to solve their problems using machine learning. You have many data to process. You have many unsolved problems that industries and practitioners try to apply machine learning on them. But the difference is that almost all the speakers in this workshop talked about and used supervised or unsupervised learning. They have used these learning approaches to solve problems, or they did something, some engineering task for these learning techniques. But in this talk, I will focus on the third main paradigm in machine learning, which is called reinforcement learning. In reinforcement learning, we mainly try to solve some decision problems, and we have a decision process to solve. We have a reward system, and we need to learn from a series of actions when we are interacting with the environment. So what is the problem? I need to address two concepts in this slide. First, what is the sequential decision-making problem? And then what is an interaction between agent and environment? Usually in reinforcement learning, or by the other way, usually in a sequential decision-making problem, we have an agent interacting with an environment, or by the other way, we have an agent, we have an environment, and with an agent inside that environment. Agent usually is equipped with two types of devices, sensors and actuators. Sensors like camera, GPS, or microphones trying to gather some information from environment and make a perception of the environment for the agent. Also, there are some actuators like my hand, my voice, or arms of a robot. Those actuators helps the agent to run some actions inside the environment. So basically, we have an agent inside an environment trying to understand the environment, receive some information from the environment, and take some actions inside the environment. Why? To solve a sequential decision-making problem. The problem is that the agent needs to make a set of decisions, one after each other, to reach a goal. For example, like playing the game. You start usually in a game, for example, in soccer. You start from initial state, and then the agents try to play, making decision, passing the ball, trying to reach the goal and scores, or reach an final or terminate the step. So you have a problem for the agent to be solved. It's making decision on all these steps. So how learning can help? Let me just quickly describe what will happen when an agent is interacting with an environment. The agent starts by observing the state of the environment using those sensors. So these sensors help the agent to understand or to perceive the state of the environment. Then the agent knows on the state, it needs to take an action using a decision-making strategy, which is called policy.
using this policy, the agent decides what we should do upon the environment. After taking the action inside the environment, then a reward will be sent to the agent. So the agent will be rewarded positively or negatively, can be punished or can be acknowledged based on the action that has one specific action that has been done upon the environment. Basically, agent needs to learn from these interactions, doing some perceiving the state, doing some actions, receiving the reward, and then try to find those states that maximize the reward. Basically, the problem that should be solved is reward maximization. The goal for the agent is to maximize the reward along the period of the time using all those rewards that's received from the environment. How deep learning can help? Deep learning can help for a better and for more efficient policy learning. As I mentioned, the agent needs to make some decision. We can deploy a deep learning, a deep neural network here to train the policy. The deep neural network needs to receive the state, the output would be action, and we can have some training procedures to learn how the agent should behave inside the environment to maximize the reward. There are different deep reinforcement learning approaches, different algorithms that try to adopt deep neural networks to learn a good strategy for the agent to perform better in the environment and to learn how to maximize its reward inside the environment. The reason that we are interested specifically in these deep reinforcement learning techniques is that using deep reinforcement learning, we can have some human level performance in some particular tasks. For example, for after benchmark. Before or without using deep learning, we are unable to have such systems, such agents that train at the level of the human. I like to highlight Dreamer V2, which has been proposed in 2021. As you see, Dreamer V2 has much higher scores than a human trainer in a set of algorithms. And I should highlight that it is not only a particular algorithm, set of algorithms. This benchmark includes 56 different games, and this system can achieve much higher than a human player in those. The main benefit of using deep reinforcement learning, the main achievements that becoming interested is to having these human level performance. So it doesn't mean that there is no fault. Deep reinforcement learning based agents, all of them are software. They should be deployed as software, or they are software components that should be used inside of larger systems. So all of them are software, and there might be fault. So these faults can lead to failure or other problems. They might result in developer mistakes, wrong understanding of developer from the policy or the algorithm that should be implemented, or misusing APIs. Different faults could happen. And again, we already know that there are some faults. Again, many of you might have seen these slides and these report of faults many times during this workshop, because we already know that there are some faults inside those machine learning based applications. Let me show you a buggy version of a particular reinforcement learning agent. Here you have a problem which is called, it is the famous benchmark problem, it's called lunar lander. Basically, we have a spacecraft trying to land on the moon. You have to flag indicating the desired position for landing of the aircraft. I will show you a buggy, if I can play, that I cannot play. So we can see the behavior of a bug agent. The bug was about the interaction of the agent and the environment. As you see, agent tries to land on those specific position, but it is impossible because the interaction between the agent and the environment is buggy, and agent does not have a good understanding, actually does not have a right understanding of this information that is receiving from the environment to take the right decision. So you see, there is no crash or failure.
The only thing that you can see is that the task cannot be accomplished, and the agent fails to complete the task. So here is the healthy agent. You can see that the agent, after sufficient training, is able to land perfect on the desired position. So there might be some bugs. If you want to address those bugs, first we need to understand them. First we need to know them. First we need to have some information about them, then we can address. Basically, we are interested to know the types, symptoms, and root cause. So we ran the first empirical study to identify different types of faults inside deep learning programs. We followed a typical methodology in the empirical software engineering. We start to search about faults over GitHub inside projects that have deployed different RF frameworks and different deep RL application. Also, we have searched over Stack Overflow to see if we can find some questions mentioned by developers about using deep reinforcement learning programs, about the issues and problems that they have faced when they are trying to use it. So we have collected some samples, then we did multiple round of labeling issues and resolving the conflicts, typical methodology that is followed in empirical software engineering. After proposing a taxonomy, we ran online survey using some experts to validate our taxonomy. And after finalizing the taxonomy, we have used that taxonomy for two purposes. First, to develop a tool to identify faults inside the learning systems, and also to use those faults to seed some mutation testing techniques. So here is the taxonomy. Actually, there are when you are looking into a deep learning program, you might have two types of faults. First of all, generic programming faults. You might see these faults in any software program. You are not interested in them. Also, you may, since we are using deep neural network in those applications, you might have seen some faults related specifically about the implementation of that deep neural network. For example, some problems about the model layer, size of tensors, line, loss functions, or hyperparameters. They are faults associated to implementing a deep neural network. But you may see some faults which are specific to deep reinforcement learning. When the developer tries to implement a deep reinforcement learning technique, we have identified four main categories. Faults related to interacting with the environment, when the agent might miss the setting of the environment, or when the agent might miss the terminal state of the environment. Also, there are another category about problems that might occur when the agent tries to explore the environment. Also, when the agent tries to updating the neural network, for example, wind update tool or suboptimal network, update to frequency or output layers. Also, there are faults associated with output layers. After that, we try to propose a technique for finding faults in deep reinforcement learning application. Basically, we have followed a meta-model approach using graph transformation. First of all, we have proposed a meta-model for deep reinforcement learning application, but based on DQN algorithm. You can see meta-model here. We have identified the main components of the program. For example, the DQN algorithm, the exploration part, hyperparameters associated with the algorithm. Also, there are two neural networks, the U network and private network, that should be updated gradually and get trained. And also initializing the environment, setting and terminals. So the tool, which is called DRLinker, is based on static analysis. So the developer needs to prepare or feed the buggy code into a parser. The parser extracts relevant information from the
code to build a model of the program. This model is conformed to the meta model that I just showed you. After extracting all those information and building the model, we run a model-based fault detection. We have proposed some rules to detect those faults that we have identified in our taxonomy. Using those rules, we are able to detect some of those faults. So whenever we find the fault, we can get back to the developer, mentioning the type of the fault or some warning about design issues that we have found in the program. There is a main limitation with this approach. It is based on static analysis. We are not running the program and we are not analyzing the program when we want to do some static analysis. Just looking at the code, extracting information and reporting the faults that might happen. So we are not able to find some faults that related to the behavior of the program or that the inefficiencies or issues that might occur when the program is running. So in the next approach, we try to adapt mutation testing to reinforcement learning. I need to quickly mention that what is the idea of the mutation testing? The idea of mutation testing is to test the oracle or test suite. Suppose that we have a faulty program. The question is that can we find particular or sufficient test cases to identify that fault? Do we have such test oracle to identify the program? So basically, mutant is a valid program that behaves differently from the original one. For example, by considering a small change. Still, the program is valid, but the outcome is different. So we can define that the test can kill the mutant N if he produces a different outcome on it. So we can say that this mutation has been killed using that particular test case. So to adapt mutation learning to reinforcement learning, two questions should be answered. How to apply reinforcement learning, how to apply mutation testing inside reinforcement learning for machine learning in particular, when we know that there are some stochastic behavior. That previous talk was about those non-deterministic behavior of machine learning. The second question is that what is this test suite? Because we know that inside the reinforcement learning, there is no data set and also the testing approach is different. So what is the test suite? What is the proper test suite for reinforcement learning to adapt mutation tests? We already know that there are some non-determinism introducing factors. There are some factors inside the training procedure that introduce non-determinism. So the output we got multiple identical training runs produce different train models. We have used identical settings, identical training data, the same algorithm, the same network, the same hyperparameter, but we will end up with different models. That is the problem. There are these factors are different. I will skip this part. I just want to show that what is the result. When we are reporting a performance of a deep reinforcement learning agent, we don't see any accuracy or F1 measure or something like that. We only see the rewards. So basically in the x-axis, you are seeing the episode spent for training the algorithm. In the y-axis, you are seeing the reward. You can see that for this particular algorithm has achieved more reward and the level of reward is not. But it's not only one agent. As you see, we have imported the mean reward. Also, you can see there are some standard deviations. So basically, there are different agents. Although we have set identical hyperparameters and identical settings, but we ended up with different agents. So how we can test them? If one of them behave differently, does it mean that there is a fault there? No, because there are different agents. They might behave differently, but it does not necessarily indicate a bug or a fault. So the question is how to identify fault instances. The idea is to do multiple tests instead of a single. But the question is that, okay, what are the test cases in the case of reinforcement learning since we don't have any data? The idea is to using different models.
For example, this is those figures indicate the problem of frozen lake. The agent, the idea is that to train the agent on this original or the first environment, we can see the start position, we can see the goal position. The goal is for the agent is to find the path from the start state to the goal state without falling down to those holes. We can train the agent on this environment and then test it on different environment. The location of the goal has been changed to see how the agent can adapt himself to this environment and if this environment is able to identify those faults or mutate or kill those mutants. So what we have proposed with Ahura and Florian is to explore the space of different environments. Suppose just consider a hypothetical environment. There are two parameters associated with that environment. If we indicate those parameters, then we can indicate the parameter. So we explore the space of parameters to find proper environment. Just look at this boundary. We have found this boundary. I speak in the case of the algorithm. Every environment inside this boundary would behave the same or by the other way. If you put an agent in all those environments, the agent will behave the same. So all of them are equivalent. But if you cross this boundary, any environment defined or set outside this boundary, the agent will behave differently. So we can use these different environments to test the agent. So basic solution is that we use multiple agents, multiple mutants, and multiple tests. We call that we have two problems. We don't know how handle the stochastic behavior, and we are going to define the subcases. For the second, we went for different environments, and for the first one, we will do multiple tests. Then we will see if there is statistically different behavior between these two sets of ones. So, yeah. So we test a set of train agents. We train agents with this identical hyperparameter, identical settings. We have multiple agents. They are different, but they behave equivalent in the space of environment. If the environments are able to indicate the body for healthy agents, this is our goal. So we test the agent against different environments to see if the agents behave differently or not. In this way, we can identify those faulty or body agents. Here is one of the results. We call the lunar lander problem. There are two main parameters, the gravity and also side engine power. So here is the space of all the environments. Each point in this plot indicates a particular environment. The difference between these environments are the parameters. So we are interested to see how the agents behaves differently in these environments. Orange points shows the environment that are able to kill the mutation. The blue one shows the environment that don't kill. So basically, we found the boundary that make a distinction between the environments that can kill the agent and those that can't kill the agent. In this way, we are able to find those faulty or those mutant agents. We have employed another technique to further analyze the results. The idea is using higher order mutations. The idea of higher order mutation is combining different mutations. We have some simple mutations. Those mutations are created by injecting some real parts inside the healthy agent. If we combine them, we can have some higher order mutation. Then we can see if those testing environments are able to detect those higher order mutations or not. I just highlight that, yes, using different algorithms like PPO, and QN, and on two different environments, Part4 and lunar lander, we have successfully found two very hard to detect H1s. By combining those simple mutations, we have found two higher order mutations that are very hard to detect by the other, all those environments that are able to indicate faulty agents, we're not successful in identifying those patterns. So we need a different set of environments to identify those fault agents. So what is the next? Currently, as I mentioned with Rashid and Ahmed, we are working on a debugger for deep reinforcement learning program. The debugger is supposed to be embedded inside the deep reinforcement learning framework, so the developer has the opportunity to debug and test this program when he's developing this program. In this approach, we are using also static and dynamic analysis to check all those faults inside the code. Also, to follow the direction of mutation testing, we are going to test the challenge of multi-agent environments. All the environments that I mentioned during my talk are single-agent environments. There were only one agent inside the environment acting and performing. If you have multiple agents, for example, like soccer, you have 11 players inside it. It is very hard to address and very hard to tackle. All those approaches and results are about single agents. We expect that the challenge of multi-agent environments should be very hard to solve, and we are going to apply these mutation testing techniques. So I am done. Thank you for your attention, and let me know if you have any questions.
Maybe I'll go first myself. So my question is about the methodology. I really like that you go with the Stack Overflow to find the real problem reported by the people. Is there a possibility to actually find the plot repositories of those projects and to look at the faults that have been reported in the code? Does it help us? Were these problems or not really?
Yeah, it helps us. But let me clarify. For Stack Overflow, on the Stack Overflow, actually, you may find only questions that have been asked by the developers. But if you go to the GitHub, two types of faults you may find. If you go to repository of deep learning frameworks, you may find some bugs that developers have found, or they are thinking that they have found inside the framework. But if you look at projects that employ the framework to extend some, to develop some deep reinforcement learning project, then you may have found faults that the developer have encountered during implementing those algorithms.
Which is what you're looking for.
Exactly.
Any other questions?
When you talk about the boundaries of the environment, so how we can make sure, I mean, how we find these boundaries and what's the accuracy of these boundaries, and it seems to be also quite challenging, right?
Yeah. We have employed a heuristic based on bisection, that's by dividing all those boundaries to have and then exploring one of those. Then we have actually we try to increase the value of one of those parameters to see when the agent, when the mutation, when the mutant will be here. Then we have an environment. Then we divide the distance between the center of the coordination and that value into two halves, then there's so the basic idea is based on bisection, and I should highlight that it is only a use.
So which means that you want to scale this.
Yeah.
This also will scale
that is also another limitation is that it's limited to the type of the faults that we have injected in the program. If you come up with different faults, you might have different boundaries. And also, we don't claim that these boundaries are, for example, unique or they are optimized. We are only looking for some environments to be able to kill them.
It's very interesting. We could think also maybe of other domains other than maybe learning approach that have heuristics that can make this.
actually the space of different environments is too huge. So, yeah, it is an interesting point.
Great. Okay, let's have another round of applause.
We're almost there. Yeah, maybe it's just quick. Okay, this is it. I think we are at the end of these 2 days. They were intense, at least for me, and I hope you find them interesting. I hope you find the content useful for your research. And I won't be long. I think we're all tired. This is just really thank you. Thank you for all of you. Thank you for being here. Thank you for attending so studiously, for sacrificing somehow this weekend and being there all the session to the end. I think that's very impressive to me. So thank you very much for that. And maybe a big round of applause for yourself. And this wouldn't have been possible without our army, fantastic army of student volunteers. Really big thank you for you guys. And I think that's it. See you next year for SEMLA 2023. Have a safe return back home and safe a good start of the next week. And see you. See you. Goodbye. Thank you very much. Thank you.